went on to handle. So, welcome to LCTES. Thanks for coming. LCTES became a conference in 1998, and this is the 25th version of LCTES. Before this was LCTES, that is language compilers and tools for real-time systems. And it was started by David Wally, Frank Muller, and Thomas Marlowe. And it became a conference in 2002. And the first one being organized in Berlin with Peter Marvidal and Srinivas Devdas as the chairs. And actually this was a joint organization of Scopes and LCTES. That's why Peter Marvidal. Right? And in 2012 we added this word theory in the title. Before that it was only tools for embedded systems, and then we added theory for embedded systems. And since then it has been around the world at a lot of places, and this year we are coming back to Copenhagen. So we have set up a very rich and interesting program for all of you. Hopefully you will all like it, and it will be worth all your travel and trouble. Just after this welcome, we'll have a keynote with Professor Kader, and then we have a tea break, which is just outside. Right? There are lots of places where you can get tea. Then we have our first session on optimization inside this room, Iceland. So if you are in this room, you are in the right room. For lunch, we'll go to this Fellini Cafe, which is downstairs, right? Yes, which is downstairs. And then we have our second session, embedded systems, and then again a tea break, and then our last session on analysis and testing. And in the closing session, we'll give out the certificates and the best paper award. Right? So this is the chart for our LCTES organization. All the people who have been involved with the organization of this conference. Although it's just a one-day conference, it takes a lot of preparation, and 90%, maybe more than 90% of the work is by Professor Sui. So he has done a tremendous amount of work in organizing this. And one good sign of a good conference is the steering committee members are still a part of the organization and present in the conference and are submitting papers. I mean, I cannot submit because I have a conflict, but JJ is here, so that's a very good sign. Jason is also going to be coming today. So with this, I leave the reins to Professor Sui to take it over. Thanks.
Actually, I would like to thank all the committee members, including the steering committee members. They are very supportive through each stage of the conference papers reviewing process, how to set up all this, and also all these PC members. So actually this year we try to bring as many PCs as possible. But one thing is we know that there's an increasing number of submissions for across all conferences. So LCTES is going to be something also on the rise. And also we want to bring papers from the experts in the committee as well. So all the PC members across Europe, Asia, and Europe. So you can see we have a mixed number of middle career, early career, and established researchers across different countries. We have mixed experts from academia, from also from the industry. So we are quite happy to see that they have dedicated their actually few precious weeks in dealing with all these reviewings. So we have a very short turnaround, actually similar as previous years, around like 1 month much like 1 month's time. So mainly we had reviewing starting from March, early March, and then we move to all the reviewers and some papers reviews was almost done towards the end of March, and we have an online discussion, which is quite intensive, and eventually we send out the notifications on time. And also we have similar as previous years, we have double blind reviewing, so authors' names and their affiliations were omitted, and also we asked the PC members to try to assess the paper in a way that not trying to disclose or intentionally search their affiliations so that avoid any bias. So we have this year we have a record high number of submissions reviewed by 35 PC members, and each PC is assigned around like 3 to 5 papers. So in total, we have around 150 reviews. So for each paper, we have at least 3 reviews. So through the online discussion as well. So we follow the previous year's evaluation criteria, so mainly significance, novelty, soundness, verifiability, transparency, presentations as well. So we have 2 types of papers accepted this year. So it's following the similar practice as previous years. We have full papers, and which is it's 10 pages plus 2 pages references. And also we have working progress papers. So we have 15 papers in the full paper track, and 1 paper accepted working progress paper, and 1 invited paper. So the submissions look quite good. So we have 52 submissions. We have a submission which pretty much going up. If you see this trend, so we have sort of a similar acceptance rate as previous years. So you can see this shows the healthy trend of LCTES. We hope to grow more submissions next year. So yeah, so we have a pretty much similar acceptance rate, slightly lower than the last 2 years because we have a few more submissions. And submissions by countries, so there's no surprise, China, Singapore, US. So basically the submissions most come from there, and followed by Korea and Germany. We have accepted papers, also similar based on the portions of the submissions. So and also for the MAN areas in the call for papers, you can see that programming languages still ranks top, and interestingly, we have a number of submissions in the area of large language models. So there's no surprise because this topic is quite trendy. So I hope later on, because this year we had a new topic added in the call for paper. So we hope we're going to keep the topic in the following years to attract more interesting papers. So for the next few areas, so architecture, energy, operating system compilers, IoT, and mobile. So this is the sort of subtopics. You can see that privacy, security, SE for machine learning, performance analysis testing, ranking pretty much at the top. So this is the keywords. So you can see that code, detection, precision systems, embedded. So this sort of so this is the catch the spot. So yeah, and towards the end of this program, we're going to announce the best paper award. So if you want to stay until last, you will know how you get that. So conference logistics. So if you just came in today, so you can join the Wi-Fi. That's a Redison guest. I don't think we need any password. So it's sort of free Wi-Fi. You can do it. Just connect just on site. And for presenters, just make sure you contact your session chairs. Better to be 15 minutes before the talk you're going to deliver. If you're using a Mac computer, the conference organizer asks you to turn off the True Tone. Yeah, True Tone. Yeah. So that is because the video we're going to do the sort of live streaming and recording. So if this one is basically once you turn off this True Tone, the background color become a bit cold rather than warm color. So that will be better for the live recording. So if you don't know how to turn that off, once you go to the session chair, I think the session chair will help you with that. For lunch, we're going to have lunch downstairs, not this floor. And we have the afternoon tea just outside the conference room. And also, unfortunately, there are going to be 2 remote presenters because of visa issue. They can't join us on site. So they're going to present their talks in the second session. Okay, so I guess that's pretty much that. And let's move to the exciting session. So our keynote speaker will be Professor Christian Hader. He's a well-known figure in this area, particularly programming languages, software engineering. He's a main author of the well-established and popular open source tool PLDI', used for symbolic execution. And this talk is going to give us his recent topic on flooding. Okay, let us join me to welcome Christian for his talk. Yeah.
Thank you very much, Yulei, for the introduction. So, should I turn off True Tone?
Yes, yeah, if you can.
Yes.
All right, everybody can hear me all right?
Yeah.
So thank you very much to Yule and to Aviral for inviting me to give this keynote. It's really a pleasure to be here. So indeed today I'm going to talk about fuzzing, and I'm going to offer some reflections, and I'm going to discuss some of the open challenges as I see them. Of course, this talk is going to be shaped by my own experience working in fuzzing. And I've actually done work in fuzzing for many years now. All right, you did the slides did switch. So this is actually the first paper that I wrote on fuzzing. It's on white box fuzzing, also known as symbolic execution or dynamic symbolic execution. And yeah, time flies. So it's almost 20 years since I've written co-authored this paper, and yeah, it also has a cool title, I think. So since then, I've continued to do work on fuzzing, on all forms of fuzzing. So in terms of, I've continued to do a lot of work on symbolic execution or white box fuzzing. And if you look at this, the title of this recent paper, you can actually see where, what my dream is still is to run symbolic execution forever. I've also done a lot of work on gray box fuzzing recently, and that's, for instance, one of the projects that we worked on was on high throughput fuzzing for network applications. And most recently, I've started to look at black box fuzzing, particularly grammar-based fuzzing, and particularly in the context of compiler testing. Although this paper that I showed here, in which I will discuss a bit later on, is not on compiler fuzzing. So the three colors of fuzzing are white, gray, and black. But I think actually fuzzing is much more exciting than that. So I added a splash of colors here to the right. So I think is everyone pretty much familiar with the different forms of fuzzing? So I see most people nodding, but just in case there are a few who are not, I'm just going to do a very, very quick introduction. So black box fuzzing, the reason it's called black box is that you're treating the system as a black box. You're just observing essentially how it behaves based on these interactions with it. And perhaps the most common form of black box fuzzing is grammar-based fuzzing. So the idea here is that you have a grammar like this one, simplified JSON grammar shown here, and you are going to then work it randomly, and you're going to essentially expand all the non-terminals until you manage to generate an input like this one. And of course, you can generate many inputs to test your program with. And black box fuzzing has many success stories. I'm going to mention a couple of them. So I mentioned already compiler fuzzing. So a project like CSmith and EMI are based on grammar-based fuzzing. In the case of EMI with some other ingredients as well. But very successful. Found hundreds of bugs in mature compilers. Also very successful in the context of database testing, for instance. The SQL Answer system is one such example. Gray box fuzzing now is perhaps the most popular form of fuzzing these days, widely used in industry. The idea is that you start with a set of inputs. You're going to select an input. You're going to do lots and lots of mutations, and then you're going to measure whether these new inputs get more coverage to the program, and if so, you're going to add them to the input queue, and you're going to iterate until your time budget is over. And that's a form of gray box fuzzing called the coverage-directed mutation-based fuzzing, which is, I would say, the most popular form of fuzzing these days. And then, in terms of success stories, there's a couple of examples. AFL really has revolutionized gray box fuzzing and has a long list of trophies. And you may have heard about Google's OSS Fuzz, which is actually a fuzzing platform where they actually run many of these gray box fuzzers and looking for bugs in open source software. And actually, they managed to find today like an impressive number of bugs using these techniques, over 36,000 in over 1,000 open source programs. So now, white box fuzzing, also known as I said symbolic execution or dynamic symbolic execution, the idea here is to systematically explore paths through the program using a constraint solver underneath. So what you're going to do is that instead of running, let's say that I have this piece of code here, instead of running it on a concrete input like k equals 10, I'm going to run it on a symbolic input, all right, which initially is allowed to take any value. And when I reach a branch that depends on the symbolic input, either directly or indirectly, I'm going to check the feasibility of each side of the branch, and if both are feasible, I'm going to fork execution and follow each path separately. So for instance, here on the true path, I'm going to have the constraint that the branch condition is true, so k is it mean, and then I'm going to continue execution in the same way. I mean, here I just return -1 and I'm done. But for instance, on the false path, where I have the constraint that the branch condition is false, so k is not in mean, I'm going to continue execution, and I'm reaching this other branch, k less than 0 again. I'm going to check the feasibility of each side of the branch. This time I do have a constraint on this path, which is k is not in mean, but of course both sides are still feasible. So I'm going to follow both. I'm going to have the constraint that the branch condition is true on the true path, and I'm going to return -k, and the constraint that the branch condition is false on the false path, and I'm here, I'm just returning k. So now, at the end of each of these path traversals, I can take the set of constraints that I collected. For instance, here I have k is not in mean and k is less than 0. I can ask the constraint solver for a value. Let's say it gives me k equals -5, and now I have an input which is guaranteed to follow the same control flow path that was followed during symbolic execution. So in terms of success stories, again, there are many. For instance, Microsoft Sage is credited to having found 1/3 of file fuzzing bugs during the development of Windows 7 using this technique. And Yule mentioned CLI, which is an open source tool widely used in both research and academia. And because we're maintaining CLI and maintaining and developing it in my research group, you can see I also have a nice sticker here on my laptop. I'm going to take a very quick publicity break, if you want, to tell you a bit about CLI. So it is a system for symbolic execution or white box fuzzing. It works at the level of LLVM bitcode. So as long, we've used it primarily for C, but it also has some support for C++, for Rust. In fact, as long as you can compile your code to LLVM bitcode, it's going to work. I'm quite excited about the impact that CLI has had both in academia and industry. So in terms of academic impact, this work led to a couple of Test of Time awards. Lots of citations, but I think what's very exciting to me here is not the number of citations, but the fact that they actually come from so many diverse fields, like security and programming languages, which actually shows in and CLI is useful to the community. And we've also seen growing impact in industry. So for instance, here I mentioned some of the companies that have published papers or given talks or wrote blog posts, about experimenting and using CLI for their own systems. And we have an active community, but we're always looking, for more interested people. So definitely, one thing that I hope that you'll take away from this talk, maybe check out CLI to see if it's useful for your own research. We also have an ongoing workshop series on CLI. So we've just had the 4th workshop in April in Lisbon, co-located with ICSI. And the first 4 editions, have gathered together over 400 participants to date. So it's quite an active workshop series. So definitely consider a future edition if you're interested in this area. All right. So now I'm coming back to to my talk on fuzzing. But before actually I talk more about fuzzing, let me actually talk a little bit about manual testing, because I think it's important to understand how developers actually test their programs in practice these days before seeing if we can help them with fuzzing. So 10 years ago, 2014, we conducted this empirical study where we analyzed 6 popular open source systems. We looked at 250 patches in each of these systems, and we tried to understand how developers are testing, their code as it evolves. And the one-line conclusion was that unfortunately, lots of code was being added, or modified without being tested, sometimes not at all. So now, 2024, I was actually quite interested to see if things have changed, whether we are doing better. We've seen many changes, like CI frameworks, like fuzzing, coming into play. So I had a very good master student who tried to look and to replicate and to extend this study to the latest decade. And we actually looked at the same 6 systems plus 3 more. So you should recognize many of these systems. They are widely used, things like APR, binutils, curl, git, LCTES, memcached, Redis, Vim, and 0MQ. So these are the time spans that we considered in this study. The hashed areas to the left are the ones that we considered 10 years ago. So this is basically the rest is since then. And we have 3 more systems where they don't have any hashed areas. So in total, we looked at between 3 and 14 years of development time per project for a combined 78 years of development time. So quite a lot of data. So we have actually many interesting conclusions. I'm just going to give you a couple which are most relevant for this talk. So first of all, I guess you're not going to be surprised to see that systems keep growing, okay? And here you can see essentially for those periods considered, like the evolution of the executable lines of code for these different systems. And you see that they add a lot of code, right? Both in absolute values and in percentages. I think that's definitely a problem here, that's a lot of code bloat here. I mean, if you look at these systems, their core functionality in some ways has remained unchanged. Of course, many things have to change, but perhaps not at this rate. But, that's the topic for another talk, and, although I'm happy to chat to you during a break about this subject. But code does grow tremendously. Now, how do the test suites keep up, all right? So we have a mixed, picture here. So a bit of big news, good news is that the coverage achieved by the developers' test suites does increase over time, right? Although we do have one application, Redis, here, where it does decrease. So these are basically line coverage and branch coverage over time. However, despite the fact that they do increase over time, which is good, I think we have to consider 2 things. One of them is that line and branch coverage are quite a low bar, of course, for testing. But the other thing is that some of these applications start from very low values to begin with. I mean, look at binutils, look at LCTES, right? Look at even Vim, right, which starts from just above 40-something% for branch coverage. Although Vim, as you can see, they've done a lot of progress in this period. So that's overall coverage, right, of the test suite. I'm actually more interested in patch coverage, all right? So how well patches are tested. And the reason I'm interested in that is that if you look, for instance, at the security vulnerabilities that made the news, things like Heartbleed, right? I mean, these security vulnerabilities have been introduced by software patches, right? So I think that that's really important to, and challenging to actually test the software as it evolves, right? And here we actually looked at how well patches are tested. So what we do here, we measure patch coverage. So what's patch coverage? Let's say that a patch modifies 10 adds or modifies 10 lines of code, all right? Now I look at the test suite, how many of these lines are exercised, right? If it's 6, it's 60% patch coverage. If it's 2, it's 20% patch coverage. So here for every of these systems, I'm grouping these patches by patch coverage. So for instance, the ones in dark green here are 100% covered, given this metric, while here in the dark red, they are 0% covered. And then we have like things in between. So I think we have a big problem here, right? A lot of code continues to be added or modified without being tested. Sometimes not at all right? I mean, if you look at this dark red. And in fact, things are even a bit worse because here I treat every patch equally. But as you can imagine, a patch which has like, 2 lines of code, it's much more likely to get high coverage than one that has like 200 lines of code, right? And the other thing, again, this is a very low bar. A lot of this coverage, in fact, it's incidental, right? They're not really testing the patch, the behavior introduced by the patch. They're just touching the lines of the patch. So, can fuzzing help? So I think the answer is yes, but. All right, so I'm going to tell you about some of the challenges. So I'm going to start with the fact that fuzzing tends to generate either too many invalid inputs or too many valid inputs, okay? So I think with too many invalid inputs, it's more easier to understand that this is a problem, right? So for instance, with gray box fuzzing, you're generating a lot of random inputs. And even with white box fuzzing, where you're very systematic, if your search space is dominated by invalid inputs, well, that's what you're going to systematically explore. So often what happens is that, with these fuzzing techniques, particularly gray box and white box fuzzing, is that you're going to generate lots of, ugly looking inputs that actually are invalids, okay? And they don't make it to the core functionality of the system. And a lot of the research, in fact, in gray box and white box fuzzing try to solve this problem. How do we generate, meaningful inputs? And there is a lot of research in terms of mutation strategies, exploration strategies, better coverage metrics, eliminating redundant explorations. So I won't have time to go into too much detail here, although I will touch upon one of the techniques, exploration techniques, later on. So now, interesting enough, for white box fuzzing, you actually have the opposite problem, if you think about it. For instance, if we look at grammar-based fuzzing, right, you have a grammar. I'm going to traverse it randomly. By definition, I'm just going to get valid inputs, all right? And what's the problem with this? Well, let's actually first look at consider, the inputs accepted by the SUT, right? The SUT stands for System Under Test. The inputs generated by the grammar. So in theory, these are the same, right? Now, in practice, things are a bit more subtle, okay? They are actually, these two actually differ in practice, okay? So what are the implications of this? So the biggest implication is that we're not going to explore this top left corner, right, which are inputs accepted by the SUT but not generated by the grammar. And why is this a problem? Well, this is a problem because you are missing the kind of potentially critical bugs where the SUT is incorrectly accepting an input that it should reject. And of course, if this input is, for instance, malicious, right, in a security context, that's a big problem. Another thing that this, this left, upper left inputs can reveal are bugs in grammars, right? Because there may be actually, there is an issue with the grammar because it's unable to generate some valid inputs, okay? Now, we also have this bottom right corner where essentially these are inputs generated by the grammar which are not accepted by the SUT. These are less interesting in practice. I won't go into detail, but one, perhaps the more important thing is that these are already generated by grammar-based testing because they can be generated by the grammar. So here's, and then you also have like these slightly invalid inputs, right? Which are actually you really like to explore because many of the bugs are there. So that's actually quite an interesting point, and it's not very easy to formalize this. So if you generate completely random input, so as I said, I'm working on compiler fuzzing. So if I manage to generate like a random string that crashes, you know, GCC and Clang, the chances of that input being fixed, of that bug being fixed by developer through this bug report are very close to zero. And that's because compiler developers have so many bugs to deal with, and they're going to deprioritize essentially like just some unrealistic input, you know, that pretends to be a program that causes an issue in their compiler. I mean, of course, it should be fixed if they have time, but that's often, you know, time is a big but. Now, if you give it like a program that it looks almost correct, then yes, they are going to pay attention, and I can tell you firsthand, you know, about these things because, you know, they think that this is realistic, right? So that's what I mean by kind of like, you know, slightly invalid inputs. So here's how our recent idea that we've experimented with that tries to generate this kind of interesting inputs with grammar-based fuzzing. And this is grammar mutation, right? So I mean here, like, we actually mutate the grammar. So I take my grammar G and some SUT that I want to test, and then I mutate this grammar G to generate a grammar G prime. And then I'm going to fuzz, you know, the SUT using G prime instead of G prime. And now I can actually look for these non-G inputs, which are generated by G prime, that are accepted by the SUT. And of course, I can try many, many different mutant grammars. To make things more concrete, here are the kind of mutations that we've experimented with, but of course you can try many other things. So just as one example, you know, if we have a repetition 1 too many, we change it into 0 or more, right? So 1 or more to 0 or more. Or we maybe add an extra choice as part of a rule, right? So perhaps the key thing though here is that these mutations are monotonic. And actually, initially we thought that, you know, they shouldn't be monotonic, but the reason for making them monotonic, so what I mean by this is the language of G prime is a strict superset of G. That's actually because you want to be able to generate any input that G was able to generate and then do these localized mutations, right, to any input. So this seems actually quite useful for generating the kind of inputs that I discussed. So we implemented this into a system that we call Gmutator. We tried it for grammars, for JSON, for Lua, for URL, and for XML. We took, and for various SUTs, you know, for these languages. And actually, we did find 10 bugs that were confirmed, 6 already fixed, which are out of reach of regular grammar-based fuzzing. And interesting enough, we started Antler. If you know, it's like has a repository of grammars for many different formats. And that's what we use here. And actually, we did find also 3 bugs in these grammars, which were all fixed to date. All right. So I'm going to move to a different part of my talk where I'm not going to focus not on overall testing, like I've just discussed, overall testing of a program. I'm going to look specifically at testing changes, okay? That, as I discussed, a lot of the problems are introduced by changes. So, can fuzzing enable better testing of software changes? So again, we have a yes, but. So one big issue is that fuzzing is often not agile enough. So if you look at most of the fuzzing techniques being developed out there are for whole program testing, all right? And in fact, most of the benchmark suites that are in use measure global metrics. How many bugs did you find in this program? How much coverage have you achieved in this application? As opposed to essentially how well did you test this patch and whether you found bugs in that patch, in that code change. Now, there has been good progress recently on these techniques, but I think the results are still poor compared to whole program testing. And I say here, one reason is that having done both, testing doing like whole program fuzzing, it is easier than doing patch testing. This being said, there are actually good opportunities for for testing changes, patches. And of course, one thing that you can do is targeted exploration, right? So these are two pieces of work that have looked, so that's a catch which we developed, which tries with symbolic execution to target, with various heuristics, the patch code, and that's the AFL Go system that was developed with the same goal, but using gray box fuzzing. And the other direction that you can exploit is to reuse previous analysis results, right? And this is what this running symbolic execution forever had to do. So, if you analyzed your system for version 1, then you actually can reuse the results to do a much better, much quicker exploration of in version 2, right? And we're also looking to try to do something similar like to this for gray box fuzzing. So let me actually show you one technique for targeted exploration that we have developed. So we're trying to prune the search space unrelated to the patch. So suppose that you have like this call graph, and our patch is here, right, at the bottom. So now, you agree with me that in many cases, right, the code where the patch is has nothing to, there are many, it's unrelated to a lot of other code, right, but of course not all. So let's say that, I knew that in this call graph, foo, zab, and buzz have nothing to do with the patch, then, well, I could just eliminate them, and now I can really focus my fuzzing on the piece of, the part of the code that really is relevant to the patch. Now, the problem is that if you want to determine precisely ahead of time if a part of code is unrelated to another, this is very hard, okay? And in fact, what we observe that often most computation in a code fragment is unrelated, but not all, okay? So our idea, which we call chopped symbolic execution, is as follows. Instead of trying to make this determination statically or ahead of time, which is very hard, we're just going to have a guess, right? Maybe this is by some lightweight analysis. Maybe this is even manual in the when you do in a certain context when you have developer involvement, and then we're going to speculatively skip these code fragments, right? Eliminate them essentially from the program, and only if we discover later on that there are side effects, what the code has done is actually turned out to be important for my execution, I'm going to come back and try to execute the relevant paths through the skipped code. All right, so let me show you how chopped symbolic execution works. So you have, let's take this example where I have my input A, which is symbolic, and I also have this global variable Y, which I initialize to 0. And then this is my main program. I start by calling F. Then I have these if statements that reach these targets, target 1 and target 2, which are essentially my patch, if you want. And this is the function F. So here it's really trivial. It only has one if statement, but in reality, it could be like a huge piece of code, right? So now, let's imagine that this huge piece of code, which here is just like one branch, it's actually not needed. So if that's the case, maybe, yeah, let's skip it. But before we can skip it, what we need to do is a couple of things. First, we need to actually compute the ref set of main. I want to know what memory location may be read in this code. Okay, so here is, for instance, A and Y. And then I want to know what memory location may be written by the code that I want to skip. So the mode set of F, which is Y. All right, so this can be done statically. You do need points to analysis. We're very happy to use Euler's SVF system for that. And we have a few other tricks that are, which we can exploit in the context of symbolic execution. But I'm not going to focus on that. Let's say that you made this determination. So now what we're really interested in is basically the intersection of the two. So we're interested in these dependent loads. We're interested in any memory locations that may be read in the main part of the code, which may have been written in the skipped code, right? That's what can get me into trouble if I skip the code. So with this in place, I can start symbolic execution, all right, as usual. So my input is A, initially is anything. When I reach F, I just skip that code, okay, which could be, again, like hundreds and hundreds of lines of code, could actually have a huge number of paths. Often it's exponential in the number of branches in that code. So I skip it, but I do take a snapshot at that point so that I can resume execution if I need it later on. I remember the program counter, the stack, the path constraints, and so on. Then I continue execution. So I reach this if statement, if a greater than 0, both sides are feasible. So symbolic execution is going to explore both. Let's see what happens on the false path. Well, on the false path, I had the constraint that A is less than or equal to 0, right? The branch condition is false. And I continue execution. And now, I'm already very happy because I reached target 2 without having to execute a single line of code in F. I could have had like a huge number of paths through F where I'd have wasted a lot of time. So now I can just don't need to do that. Now, things are not always as rosy. So, on the advanced side here, I'm actually going to reach this dependent load. So now I'm asking, like, is Y non-zero? Well, I don't know, because Y could have been written by F. So now I actually do need to go back to F and see what has happened. But actually, do remember that I'm interested in what has happened to Y when I reach this point where I already know that A is greater than 0. So that's really nice, because now I can only execute F symbolically under the assumption that A is greater than 0. And under this assumption, only this path is feasible. So I communicate the fact that Y was set to 1, so now I can actually reach target 1. So we've had a preliminary, evaluation for this, and actually we didn't do it for patches. We did it for reproducing security vulnerabilities, but it's a very similar problem. You have some target parts of the code where you think the problem is, and now you try to generate inputs that reproduce those issues. And the bottom line here is that when we compared CLI with this CHOP symbolic execution implementation chopper, you can see that for 3 of these CVEs, for instance, like, CLI either timed out or ran out of memory, while skipping so much code, we were able to reproduce these vulnerabilities in a very short time. All right? So now, I'm going to go to the last part of my talk where I'm going to say that fuzzing also often is not thorough enough. So what do I mean by this? So by this I refer to actually this oracle problem, right, in software engineering, or software testing in particular, where you try to determine if an execution is correct, right? So I can generate lots and lots of inputs, but how do I know, basically I run them, how do I know if I found a bug? So now, of course, the easiest thing is to find generic bugs. Null pointer dereferences, buffer overflows, use after free errors. There are lots of them for C and C++ code in particular. And in fact, if you actually look at, I mentioned OSS Fuzz that found over 36,000 bugs, right, and over 10,000 security vulnerabilities. Well, those security vulnerabilities all involve these problems, right? Now, if we're moving away from C and C++, or if basically this fuzzing techniques manages to get rid of all these vulnerabilities, can we still use fuzzing to do more, right, to check other kind of properties? And that's hard, but I think it can be done. I also mentioned here that, of course, we also always have the issue of fully verifying software. But I think, as you know, this is extremely expensive. Yes, there are systems that have done it, things like ComCert, things like SEL4. But we're talking about years and years of PhD level expertise and specifications typically much bigger than the code itself, right, that went into those systems. And they're still not competitive in many aspects with the non-verified counterparts. So is there something in the middle? I'm actually very interested in my research in this question. And I'm going to show you one thing that we've done in this space recently. By the way, in the middle, we have this partial relative correctness. So we give up on checking full correctness, right? But we also want to do more than just generic errors, okay? So I'm going to look at one thing that we've looked recently are patch specifications, right? Also, this relates to what I've just discussed, the fact that we do want to test patches comprehensively. So what's a patch specification? Well, a patch specification is simply a property that encodes cross-patch properties. So, the version, so let's say like, in the version after the patch, I have this variable out. And now I say, look, I know that the patch should have, the way it has computed out, now it should be the value that it had at the program point in the previous version, so this outprev, plus 1. Okay? So that's an example of a patch specification. So now, sure, you can write these patch specifications, and in some cases, actually, they are easier to write than a regular specification, right? These absolute specifications, if you want. But then, how do we use them? Okay, we need to be able to refer to the, to outprev in some ways. So here is where product program come to play. Anybody knows about product programs? All right, so product programs are something that comes from the security community, right? So at a high level, they're just a way to merge two programs into one, typically two program versions of the same program with itself. And the reason they are used in security is to reason about these hyper properties, right? Things like non-interference, where you actually need to analyze not a single execution at a time. You need to analyze pairs of executions to be able to determine if there are any security leaks, for instance. So in that context, you basically just do the product of a program P with itself, all right? So here we're interested in terms of patch specification and patch testing in whether these product programs can work for multiple versions of the program, whether they can be constructed automatically for large programs, and whether they can facilitate the writing of patch specifications. So let me make things concrete. Again, I'm going to use this very simple example. So if I have in the previous version something like x equals y minus 1 and z equals x over 4, and in the current version I change x over 4 with x shift 2, right? Then the product program is going to look something like this. I'm going to rename all the variables in one version. Let's say in the previous version, I'm going to add the suffix underscore prev, and I'm going to basically interleave these statements, all right, in the two programs. So very easy. So once I've done this, now this patch specification like z equals z prev does make sense. And in fact, I can use symbolic execution, I can use gray box fuzzing, I can use any techniques that I out of the box on this product program. Now, of course, the construction of a product program is more complicated when you have like constructs like loops and function calls, but it can be done, and our ongoing work is quite positive in terms of the ability to do this for real programs. So let me just end by telling you about some preliminary experience that we have with these patch specifications. So we wrote patch specifications for several patches from this core bench suite of regression errors. And what we did, we constructed test driver around the functions involving patches, and then we use AFL++ and CLI to look for violations of these patch specifications. So let me show you a patch in LS, okay, for which we wrote patch specifications. So the patch was in this make link name function, okay, that takes a name to a file, and then the name of a link, of say a symbolic link that you want to create, and then it returns the full path to the symbolic, to the link, right? So if you say a/b/f.text and g.text, it returns a/b/g.text. And the patch that we looked at, the commit that we looked at, had the following message. It said, do not hardcode / use this absolute file name and their len. Instead, use stp copy, stpn copy in place of strn copy and str copy. This was supposed to be a refactoring patch. Okay, you can also tell it from the commit message. And here's the actual patch. You don't need to understand it, but you can see that it's doing what the commit message was saying. It's using, instead of this equality against /, it's using this macro, is absolute file name. Instead of doing this third chart to look for the /, it's using this function dirlan, and then it's replacing essentially stp n copy and str copy with this stp copy, stpn copy. okay, which is supposed to do the same thing. We wrote 3 different patch specifications, so these simple asserts for this patch. I'm going to focus on one of them, the most obvious one, where we say that because this is a refactoring, we want in the end, the outputs to be the same, right? So if I compare P, which is the pointer to the string that this function returns, and it should be the same as pprev under stir compare. So once we wrote this patch spec and we ran AFL++ and CLI, they both found a violation quite quickly. So this is actually one input that was generated /a for name and the link name x, so quite a simple input, but it does show a difference between the two. And this was a bug that made it into a release version of LS. What happened is that the user then reported this bug, and then the developers fixed it. But the bottom line here is that, of course, with these very simple patch specifications, the developers would have found the bug before making it into a release of LS. So here is actually the patch that the developer pushed in response to this. Again, don't need really to understand it, but it's dealing with some corner cases there. Interesting. So now what we did was to incorporate this patch and repeat the process. Okay? So see, okay, can we find more patch violations? And we didn't expect to find any more, except that we did. And here is basically another set of inputs that were generated by FL++ and CLI. So this time this involved these double slashes. Okay, so we looked at this difference. So the two versions did different things. We looked at the so we looked at this bug, and we believe it's not really a bug, and that's because if you look at the POSIX specifications, it tells you that double slashes are the same, can be used for single slashes. But I think you agree with me that developers, if this meant to be a refactoring, they should have documented this test case. Ideally they would have added such a test input to the regression test suite, to make sure, and to communicate the message that this was an intended patch, maybe, an intended change in behavior. But nevertheless, so the patch was still violated by this input. So the final thing that we did was to change stir compare with this path equality function, which essentially normalizes multiple slashes into a single one. And with this, we couldn't find any more patch spec violations. All right, so I'm quite excited about that. I think that's quite a promising way for this kind of partial forms of functional correctness. So I've reached the end of my talk. So the only thing, because as Yule was saying, these days you even have a new topic of LLMs to the to the conference. I thought that in 2024 it's hard to have a talk without any reference to Gen AI. So I'm going to end on that note. What's the impact of Gen AI on fuzzing, right, and on software engineering in more broadly? So I see 2 possible futures. One future is one in which Gen AI was going to do everything for us. All right, so it's going to write perfect code, correct by construction. There's nothing for us to do other than kind of talk to the AI to say what you need. Now, I think that's actually quite an improbable future, except for perhaps some niche, domains here and there. I think the more likely future is what AI-assisted software engineering, right? So here we're going to see this very accelerated shift from writing code to reviewing code, right, that AI has generated for us. And I think in this future, effective fuzzing techniques will actually become even more important than they are today, given the amount of code that will be AI generated. So this brings me to the summary slide. So I hope I convinced you that manual testing is not enough, and unfortunately we're seeing lots and lots of code which is added or modified without being properly tested. I think fuzzing techniques clearly can help, but they're still not enough. They're not agile enough, they're not thorough enough. There are several not enoughs that I haven't managed to cover in this talk. So we're not there yet, but I think they can already be very helpful. And as I said, I think now with Gen AI coming into play, I think effective fuzzing techniques will become more rather than less important. So with this, I'm very happy to take questions. Thank you very much.
Thanks for a nice talk. Although you said that there are not enough, I would like to ask something that we also face nowadays when we have operating systems that also have patches, also have some unclear version of different patches, and furthermore, most operating systems are not formally verified. So how do you see that such fuzzing logics could be applied, for example, to some specific operating systems that may involve safety issues? Of course, Linux is too complicated.
No, that's a very good question, and indeed it's one of the challenges that haven't made it to this talk just because of the time constraints. But yes, I think a lot of fuzzing, so the challenge is actually using fuzzing for other application domains. So right now, I think fuzzing has started with perhaps the easy bits. There's a lot, for instance, file fuzzing has been extremely successful, and if you look at tools like AFL, like CLI as well, they are targeted toward these applications where it's kind of like user level code where you have some files typically as your input, and then you try to fuzz that. I think there are many other kind of applications which are much more complicated than that, right? Operating systems is one example. There are more. Now, one thing that I think it's very promising there is to look at automatically generating test drivers, fuzz targets for various components of the operating system. This is something that we're working on. It's quite a difficult problem. It's actually a challenge in general for testing, even the kind of system that I showed you here, because fuzzing, it's supposed to be, when you think of fuzzing, you say, it's fully automated. The truth is, it's not. Except for some very simple, some applications, some very simple I/O, interface, right? No, it's much more complicated than that. If you want to test a library that takes data structures, they need to invoke APIs in a certain order, as preconditions. That's very hard. You do need to write essentially some test drivers. It's the same for parts of the operating system. So I think actually I'd like to see the community investing more time in not just on the exploration part of fuzzing, but also in this generation of test drivers. And by the way, because we talked about LLMs already today, I think that's something that they can help, right, to be able to generate such glue code, right, that fuzzers can use. Thanks for the question.
Any more questions?
It's one.
Thank you. Thanks for the excellent talk. It was really interesting. I was just curious, when you were speaking about symbolic execution and how you follow the code flow through the application, how all the different types, have you thought about applying symbolic execution to highly configurable applications that have pre-processor directives to turn bits of the code on and off at all? That's sort of like a meta level, I guess, of symbolic execution before you get to the real code. Because things like operating systems, they are super configurable, as are complex applications. So there might be code paths that exist in one compiled version and not in another.
That's a very interesting application, a very interesting problem. No, the short answer, we haven't done this. Now, I think it's challenging. I'd be curious to talk to you to see what thoughts you have. One problem is that, for instance, with a tool like CLI, we operate on LLVM bitcode, so we first rely on the compiler generating the code. So basically, it's going to be done under certain configurations. Now, of course, you could try. That's something that you can do, right? Because CLI can also be seen as a bit of a virtual machine. So you could compile this code under different configurations. You can have different defines there. You have different versions of the code that you test. You maybe even can do some cross-checking there, right? So you can compare them. But I think it's very hard to do this elegantly and more efficiently, where you just don't do this. Without repeating the process n times. And of course, n can be very big, right? And there is research on this product lines, right? So there are certain types of highly configurable systems. There has been like research about how to sample these different configurations, so maybe it could be combined with that. But nevertheless, yeah, I think in general it is a tough problem, and it depends a bit on the specifics, and something that I'd be happy to chat about.
Thank you very much.
Thank you for the presentation. I was just curious to ask if the techniques that you showed, if in C, C++ bases there were extra challenges due to things like the preprocessor or the way code is built.
Yeah, there are challenges there as well. In fact, when we started, when I started with symbolic execution, I was actually using SEAL for the compiler infrastructure from Berkeley as to instrument the code, and that in the end is a research project, a very good one, but still it was very challenging to kind of compile the code. So with CLI, we switched to LLVM. So the nice thing is that we benefit from all the LLVM infrastructure. So basically, we start from the point of after LLVM has compiled the code to bitcode. So I would say many of the challenges are solved by LLVM. There are still challenges, of course, when we try to do various forms of analysis. Sometimes even as a research project, for instance. But these are more like engineering issues. The research project is very hard to keep up with, kind of the development in LLVM. You also depend on other tools, let's say SVF from ULE, who also tools which are also facing the same kind of issues, and now they need to be compatible. So there are all sorts of issues like that. When we construct these product programs, this actually becomes more of an issue, in terms of kind of dealing with this code, or again, when we want to generate these test drivers, whatever. Another thing is that what we notice is that if you want to do things at the level of source code, as opposed to the level of intermediate level, it becomes much harder. All right. So, for instance, this test driver generation, ideally, I would like to have C code, right, or C++ code, right, that calls into the functionality of the system. But operating at that level is much harder because there are much fewer tools that know how to deal with source code directly. I'm not sure if this answers your question, but let me know if you have any other clarifications you'd like.
Thanks. So, any more questions? So, yeah, let's join me to thank Professor Christine for his wonderful talk. Thank you.
Thank you.
Thank you so much.
No, thanks again for.
I quite like the idea, actually, the agile pathing for patches.
Sorry.
Test. On optimization, and our first speaker is Tom. He's a lecturer in the School of Computer Science at the University of St Andrews, Scotland, UK. He's interested in virtualization, operating systems, compilers, and runtimes. Tom.
Thank you. Thanks for the introduction. Well, yes, hello, I'm Tom. I'm very delighted to be here, and I'm pleased to speak to everyone. I hope you find this topic interesting. Accelerating shared library execution in a DBT. Well, firstly, just a little bit about me. Thank you for the introduction there. Just a quick slide to say what I'm interested in. Yep, lecturer, computer science, University of St Andrews in Scotland. Generally work in the area of computer systems. Core research interests are binary translation, virtualization, OS, all of the systems level sort of cool things. That's what I'm interested in. Right, okay, what's the problem then? What's the problem? So, dynamic binary translation of a program that uses shared libraries leads to a performance deficit. That's the problem, okay? So let's explore that in a bit more detail. And this graph is showing you that we've got some performance to gain here, okay? We've got something running under DBT that takes a long amount of time to run, nearly 100 seconds, and something that doesn't use DBT, native libraries, that runs much quicker, 10 seconds. So we've got this big performance gap here that we're going to try and fill, we're going to try and achieve. Right, so let's set the scene a bit. Let's see what DBT is all about. So dynamic binary translation is translating a program compiled for one instruction set into another at runtime. Okay, and this is what DBT might look like. You might have some program compiled for the ARM instruction set. You might have some DBT system running on an x86 machine, and this DBT system takes this ARM program and bit by bit, as it runs it, it converts it into x86 code, and that's how it will execute those ARM machine instructions. Much more efficient than doing something like interpretation. Bit of the terminology that I'm going to use during this talk here. ISA, the instruction set architecture. Hopefully you're familiar with what an ISA is. The host, or the host machine, is the ISA on which the translation runtime is executing. And for the purposes of this talk, I'm going to talk about an x86 host machine. And the guest, or the guest machine, is the ISA which is being executed using dynamic binary translation. And for this talk, I'm going to be using ARM as the guest ISA here. So let's look at this DBT system in a bit more depth and see how it all fits together. Well, we have some program compiled for ARM, which we now know is our guest machine. We've got our cogs for our DBT system running on our x86 machine host. And the typical way that these DBT systems work is they take chunks of the ARM, of the guest program, in chunks of basic blocks. I hope you're familiar with the term basic block. And as those basic blocks are encountered, as they're executed by the DBT system, they're translated by the DBT system into host machine basic blocks, so x86 code cache. And what's interesting, a bit of an implementation detail, is that some of the guest basic blocks are translated to one or more host basic blocks here, and anything that's undiscovered is untranslated. It's very much a dynamic thing, DBT, so it all happens at runtime. Okay, hopefully you're happy with that. And this is what a typical DBT translation runtime loop looks like. We have some guest PC, the program counter, the emulated program counter of the guest machine. The DBT system says, well, does translated code exist in the code cache? Have we already seen this PC before? No. Well, translate a block of guest instructions to host instructions, store that translation into cache, and then execute that block of code. And then hopefully next time round, the translated code is already in our code cache. It's there. We can execute it straight away. And of course, there's lots of clever things you can do to accelerate this as well. You can chain the basic blocks together. But for the purposes, this is the high-level sort of runtime flow of a DBT system. And this is pretty much how QEMU, the state-of-the-art DBT system, which you might be familiar with, actually works. Just this big loop. Okay, that's the DBT side of things. What about the shared library side of things? Well, I think we could all agree that a shared library could be defined like this, a set of utility functions that can be reused by many programs. So examples of shared libraries are libc, the C standard library, or libm, the maths library that you might link your program against. And shared libraries themselves can depend on other shared libraries as well. So like libm might depend on libc, the C runtime as well. So programs can depend on shared libraries, and shared libraries can depend on shared libraries. And this is what a dependency graph might look like between programs and shared libraries. So we've got some program that depends on libc. We've got some other program that has dependency on libc and libm. We've got yet another program that depends on libssl for crypto stuff. Libssl depends on libc, libz for compression. And there's all this sort of like complex interaction between programs and shared libraries dependencies. The idea is we have these shared libraries to abstract functionality away and reuse that across different programs. Now, how does it fit together with shared libraries and DBTs? Well, DBT systems, in general, they translate shared libraries needed by the program too. So they treat it as just one unit of translation. We've got the program, it depends on a shared library. So the DBT system will translate that program, and it will also translate the shared libraries that it depends on as well. And this happens on demand, as we've spoken about with a DBT system. As calls are made into that shared library is translated as well. And of course, this means that we also need a copy of the shared library that's required compiled for the guest architecture. So we've got some ARM program that depends on libc. That means we also need libc compiled for ARM. The DBT system does its magic, works its cogs, and it translates the ARM program into its program code, and it also translates the ARM libc into its program code as well, into the library code, and we end up with all of this stuff translated together. The situation is a bit more complex because actually the DBT system, and in particular QEMU, this is how QEMU works, it also needs to translate LD Linux, which is the dynamic loader. So it doesn't do any of this stuff itself, it just looks at everything for ARM and translate all ARM code into x86 code on demand as it happens. Okay, that's how it all fits together. And this is a problem because translated code is less efficient than native code, okay? You know, we're taking from one instruction set, we're analyzing it at runtime as quick as we can, we're generating some host code as quick as we can. We can't afford to do optimizations, so translated code is generally less performant than the corresponding native code. So the observation here is that shared libraries that programs require are usually quite common. So depending on libc, well, libc is a common shared library. Of course it is, it's the C standard runtime. libm for maths, libssl, libz, libbz2. These shared libraries, they are used by programs, but they're also quite prevalent on host systems as well, they're native versions. So let's use the host versions of those libraries instead of translating the guest versions of those libraries. Right, so this is what it might look like. We've got some program compiled for ARM, which depends on libc. We've got our DBT system, and as usual, it translates the program code into x86. But whenever we see a call into libc, the shared library, instead, we just send that call out to the native version that already exists on the host machine, the x86 version of libc there, instead of translating it like we did before. Okay, that's the idea. Now, this is the mechanism. This is where it gets a little bit hairy, but let's just bear with me on this. This is how shared libraries work in general in an operating system. In the Linux operating system, this is how the shared library stuff fits together. Okay, so we've got an application that depends on libc, and it calls some shared library function. So it calls puts, and puts is what happens when you have printf with no formatting, right? Puts a string. Now, there's this funny thing called @PLT, because the PLT, or the procedure linkage table, is the magic that connects calls in the application to shared library actual code, okay? So the PLT section looks a bit like this. It's got some instructions that when the application calls puts for the first time, it jumps out to some value that's stored in memory, and that value that's in memory is a callback to the next instruction after that. The next instruction after that does a push. That's just how it works. And then this jump here calls into the resolver. And it's the resolver's job to connect this puts to the real place. It's the resolver's job to load the shared library and get it into memory, figure out where the function is, and connect it all together. So the resolver then does this. It gets some data out of the data section. Not too interesting here, but at this point here, we actually go inside the dynamic linker. Okay, so we've gone into this resolver stub code here, and we've entered the dynamic linker, and the dynamic linker loads the dependent shared libraries. It figures out where the function is. Sorry, it's behind this thing here. Load libc, resolve the puts function, and then what the linker does is it fills in the address of the puts function in here, so that next time around, we can jump straight into it. And once the dynamic link is finished, we can go and execute the puts function, and we're done. And then, like I say, next time around, that address has already been filled in previously, so it's lazy loaded, and then we can just directly call the puts function. That's how shared libraries basically work. Now, the key thing that makes this work for a DBT system that translates a basic block on the fly is that there is always a basic block with a known address when calling a shared library function. Okay, so we can detect calls to shared library functions by detecting executions of this basic block address. So whenever our DBT system sees the execution of that PLT entry, we know that we can start sending ourselves off to the native shared library versions. And this is how it starts up. We have to parse the ELF file, we have to look at all the PLT entries, we have to look at the relocation entries, we have to connect them together, we have to figure out what shared library we have, and then we just create this mapping of shared library functions from their guest PC address to the corresponding host function pointer address. Not too interesting what goes on here. See the paper for more details. But effectively, when we load the binary for the first time, we have to detect all of the functions that we need. We have to connect them together, make sure it's all loaded, and figure out what the host function pointer is. And all of this is very much host architecture specific. Okay, and then so our DBT loop then changes to something like this, right? Our guest PC, when we come into our DBT loop, we say, is this a PLT entry for a shared library function? And if it is, if it was part of that shared library function table, we jump straight into that native code. If it's not, then we just do translation as normal. And that's how it works. That's how it all fits together. So we need to translate between the guest's calling convention and the host's calling convention. We need to move the values from the emulated guest registers into real host registers. And this is where the main problem comes in, because functions obviously have parameters and return values. And in one architecture, they have one particular calling convention. In another architecture, they have a different one. So we have to connect them together. So for the example of ARM and x86, we've got our ARM emulated guest registers here, the X registers, and these correspond to function arguments 1 to 6. We need to copy them into the host registers, RDI, RSI, and so on, to make this actually work. And to do that, we need to know how many arguments they are, what type they are. In order to do that, we have an interface description language which helps us out. Okay, so we've got like the puts function there, has one parameter, and memcopy has a couple of different parameters here. And this interface description language tells our DBT which of these arguments to copy over for which type it is. Because, you know, like if we have floating point numbers, they go into different registers than integer registers. So that's why we need an interface definition language. Okay, so just to finish off here, the results are pretty promising. It's pretty good speed ups. This is sort of like a micro benchmark about floating point operations, and you know we're getting average speed ups of 5 times when running these things. So we have a program compiled for ARM using under DBT, calling these math library functions, and then we compare that versus calling the native versions of those functions, and we get massive speed ups from that. And then for more real world benchmarks, things like OpenSSL, we get massive speed ups across here for all of the different OpenSSL benchmarks, which are built into the OpenSSL tool. And for SQLite, a popular embedded database, the internal test suite here. Apart from test 16, everything is much faster using the shared library acceleration feature. Test 16 is I/O bound, so there's some weird interaction between I/O buffers here, but each of these tests sort of like follow on from one another. So test 16 is actually a clear down operation where it's clearing out the database and getting rid of stuff. Okay, thank you very much. This is just what's coming up in this area. I'm finished now. I'm going to try and get rid of the lid. I'm going to try automatically generating the lid, and I'm going to deal with function pointers, which are a tricky subject. Thank you very much.
Thank you. Time for any questions? Yes. And there is a mic over there for questions.
A very quick question. Thank you for the talk.
Thank you.
In your comparison with the speedups, what is the baseline?
So the baseline is not using accelerated techniques that are presented in the paper. So the baseline is just that application linked against the shared library run under a DBT system as normal, so everything. And then the speed up is when we introduce this connecting to the host native libraries.
Thank you for the intriguing talk. So it can be a stupid question, but did you consider ahead of time compilation because it can speed up everything quite all the time?
Yeah, sure.
Yep.
That's a great question. So ahead of time, or static binary translation in this particular case, you can't do everything statically, right? There's not enough information statically to be able to do everything, which is why dynamic binary translation is a more prevalent technique for this sort of stuff, because there are things like indirect jumps and jump tables and stuff that you can't actually determine statically at compile time. And so there's a necessary DBT side of things to do. But static binary translation is an interesting thing, and I do have a bit of work in the area of merging shared libraries, like statically into stuff as well. So yeah, it's definitely a thing to consider. Yeah.
I'm asking this question because shared libraries are quite known already before running it. So maybe you can use static things for shared library.
Yeah, I mean, so for shared libraries, that's why this is that's the observation, is that because they are well available, it's likely that you'll have libc compiled on your host machine.
Yeah.
So let's just use that instead. Yeah.
Thank you.
Thanks. Hi.
Okay, thank you. So for the talk, I guess that for this to work, the versions of libc that are in the gas system, in the host system, must match the ones that are required by the gas system. Did you
Yeah.
have any problem requiring this matching?
There's not really. So the SO name stuff is the technical thing, how like the version stuff is done in ELF. So you have to check that the SO names match and everything. There is occasionally an impedance mismatch between some structures that are translated between host and guest. We had a problem with fstat where the size of the structure was different between an ARM machine and an x86 machine. So we actually had to discount that. And we couldn't accelerate that one without an additional layer of translation. Now, there are two things that we can do. We can ignore it and then not translate that, or we could add extra mechanisms into the interface definition to say, oh, well, you also need to like adjust the structure layout like that. In general, a lot of functions can be accelerated this way if you're able to find them and test them out.
Thank you.
Thank you.
Thank you for the interesting talk. So I was intrigued by the performance results that you got, which in some ways it makes sense. But I was wondering if you have a feel for why this is the case. So for instance, in particular, are the x86 implementation perhaps more optimized to begin with? Another way to put this question: if you did it the other way around, do you think you would get the same kind of speed ups?
Right. So yeah, and this is actually quite this example here of the micro benchmark of floating point really shows the point. And the reason is for this particular one is that when QEMU translates a floating point operation, it uses software emulation of floating points. Whereas the native version of this library is naturally just using the host, XMM registers, SSE and SSE2 for it. So you instantly get host optimizations for free for this thing. So that's why there's a massive speed up for these things, because you're using the native code for that. Now, these speed ups only occur on functions that are going to be compute bound. Okay, so you spend a lot of time in the native function itself, which is why things like OpenSSL get a great speed up, because the majority of work done here is in the library itself. And so when you call into that library, you're spending all your time running super optimized native code, and that's where those speed ups come from.
So you'd expect to see it essentially the other way around as well.
Exactly, yeah.
The way QEMU.
Yeah, for sure.
Thanks a lot.
Yeah, thank you. Thanks, great question.
Thanks a
Thanks.
Okay, let's go on to the second talk. So a lot of questions about this one. So very interesting. Okay, our next talk is by Dr. Matthew Martin. He is a professor of computer science at the University of Perpignan, France, and co-founder of the Humanis company. It works on the safety of ML models. He specializes in static analysis and numerical precision.
Yeah. Here's the microphone. Okay, thank you for the introduction. So this talk is about the implementation of neural networks on fixed point architecture. It's a joint work with Dora Ben Khalifa. Okay, so very quickly, the problem is quite simple. It's just like to put a bull in a China shop. So the bull is the large neural network, and the shop is a little embedded system, either a microcontroller or FPGA. Okay, and as you know, neural networks have more and more parameters, millions currently or more, and so the difficulty is to fit them in these small architectures. So what can be reduced? First, people do pruning, that is, they remove some weights. This is not, it's a very interesting topic, but this is not what I'm going to do to present in this talk. The second solution is to reduce the size of the weights, that is to play with precision. And again, there are several ways to do it. You can either reduce the precisions of all the parameters using, for example, 16 values on 16 bits or even less. You can also do mixed floating points precision, and there is a lot of libraries integrated to TensorFlow or to the other libraries to do that. And a third solution is what we are going to see in this presentation, is to use fixed point arithmetic. Actually, when you use fixed point arithmetic in the implementation, it's only integer numbers, and so it's far more easy to handle from a hardware point of view. You have, it's faster, you use less memory and energy, but you have the price to pay is that it's more difficult to generate the code. So this is what we do in this work, and another originality of our work is that we have error thresholds which are guaranteed. That is, we can guarantee by our method formally that the error on the fixed point network is less than some bound given by the user compared to the original network. Okay, so how do we do that? To give you an overview, we have, so it's done inside a tool called Poppins. There is 5 main steps in this tool. First, we take a TensorFlow model and we extract it. We make our own intermediary representation. We extract the weights and so on. Then we need to know the ranges of the variables of the value inside the network at each point. So we perform a range analyze. Currently, it's an under approximation computed dynamically. We execute several times the network on the input set, and we compute the convex hull of what we obtain on the result. Ideally, it should be a static analyze, but it's difficult to implement a very accurate static analyze for this. And next, once we have these ranges, we generate a set of constraints. For those who know, it's a MILP, mixed integer linear programming problem that we have. So it's a set of equations. I can see it there. It's a set of equations of inequalities between linear expression among integer quantities only. And there are min and max. So it's not a pure ILP problem. Okay, so in practice, we give this system of constraints to Z3, but we could use another solver. And once we have the answer, we use it to generate a fixed point code. So the outputs of the constraints of system are the precisions that we must put for all the weights and all the intermediary results computed by the neurons. And we generate this fixed code using, currently we use the fixed math library to do that, but we are working on a new implementation where we use the AP fixed library because we want to generate FPGA code using VTs. Okay, so this is what we generate from the original TensorFlow model. And the difficulty is to find the formats which are somewhere in the operation. This is a cast from one fixed point format to another. The difficulty is to find this value, and this is what we obtain from the system of constraints. Okay, so in details, how does it work? Well, it's rather technical. It is detailed in the paper. Just to give you an intuition, I will only present this for fully connected layers, but there are other layers introduced in the article. So a fully connected layer computes some output y in function of the weights of the network w and of inputs x. Okay, and we can compute the error. We can bound the error on y in function of, I'm not going to detail this expression, but in function the maximal value of entries, the maximal value of the weights, and the maximal errors on the weight and on the entries. This is the four parameters of this equation. And knowing also how the errors can be propagated in the fixed point arithmetic, we can deduce from all these constraints which say that the precision of some neuron must be greater than this equation in which we find the accuracy of the output, the accuracy of the most significant bit of the inputs, and some static parameters. So we generate constraints like this. We are going to put a threshold on the last layer, on the outputs of the network, and going backward with these constraints, we will compute the accuracies of all the neurons in the intermediary layers up to the input of a network. Okay. There are theorems in the paper and proofs of all these formulas. Okay, and so we can do it for all, for a certain number of layers, and using this, taking a neural network, we can generate a full system of constraints for it. Okay, so as I mentioned, this is implemented in the Poppins tool, and we have experimented on a certain number of networks, going up to 10,000 parameters. Okay. The first graphic, I like this one. It's interesting. You have on the x-axis the accuracy threshold, which is required by the user. So we want to have 12 correct bits on the output, or 11, so on. And in green, it's just the threshold. The accuracy is on the y-axis. So this is just the function 2 to the power minus x. So it's the accuracy threshold. If the measured accuracies is above the curve, then there is a safety problem. Our method is not safe. To be safe, we have to be below. But if we are too much below, it means that we do not have optimized enough the system, but the goal is not to have the most accurate network. We want to have the network which consumes the less resources as possible, so the worst network, which stays below the yellow curve. So we want to approximate the yellow curve by below without being never upper. And it's rather the case in these representative examples of executions. On the right, you have a measure of CPU and memory used by the fixed point, the second is timed the second bar, and the floating point execution. So it's rather the same there. But when we go to microcontroller, here it's a STM32 microcontroller. Well, we can see that we use far less resources in fixed points. On the left, it's the time, and on the right, it's the energy consumption. And more importantly, there are several networks from our benchmark that cannot pass in floating point. We cannot load them and execute them on the board. It explodes. But we can do it in fixed points. Okay, so I will conclude very quickly, just to say that we want to add more layers and to our tool to compare. Difficulty for comparison is to have methods with formal bounds. We want to mix pruning and quantization and go to FPGA. And our goal will be to be able to embed segment. Here is an example of application. It's a semantic segmentation using a neural network and a UNet. So this is the kind of network that we would like to put on small embedded system. Thank you for your attention. Yeah. Yes, this is the accuracy threshold set by the user. I say I want to have 6 or 8 bits correct on my results. And this is the measured error on some executions. So the threshold is, if I want to have 9 bits, so the error must be less than 2 to the power minus 9. So this is the green curve. So if I am above, I am wrong. I must be below. But if I am too much below, it means that my system is not optimized. That if I use 100 bits for all the computation, it's easy to be below. The goal is to stay below using the less number of bits as possible, so as few bits as possible. So I want to fit to the curve by below while never passing it.
Okay, thank you. Actually, I couldn't understand the y-axis.
Okay.
But let's take it offline.
Hello. You really impressed me in the constraint solver, and I'm also doing some works in the fixed point arithmetics. And I would like to know if the constraint solver was executed statically or it's run on a sampled input.
No, we consider ranges of inputs. So the constraints are computed for the worst case of all the range of input that we consider.
Okay, thank you. And I am wondering if is the layers weight being replaced with fixed point or
if the what? The layer? Okay.
Oh, the layer. Okay, thank you very much.
Can you repeat, please?
I am wondering if is the layers weight being replaced with the fixed point or the inputs?
Yeah. Both.
All of them?
Yeah.
All of them. Okay, thank you.
Thank you.
Thank you so much.
Let's move on to the third talk of this session, and this is by Hill. She's an
Hello, I'm Son Young-ha from Kyung University, and thank you for the introduction. So in this talk, I'd like to introduce our work on tiny seg model optimizing framework. So tiny machine learning is to enable machine learning models on tiny embedded systems like Arduino Nikola Vision on this slide. So the size of this device is just 2 centimeters by 2 centimeters long. And these tiny embedded systems often use a low-power microcontroller with a very small size memory. So thanks to the benefits in various aspects, tiny machine learning is getting more attention in both industry and academia. However, in tiny machine learning, small memory size is regarded as the main limiting factor. So while the tiny embedded systems has a memory size of less than 1 megabyte, state-of-the-art machine learning models are much larger in size. So it is very important to optimize the memory usage of machine learning models in tiny machine learning. So our target task is image segmentation, which is to classify each pixel of input image into a certain category. So UNet is one of the most well-known image segmentation networks. So this network has this hourglass-like structure with these long skip connections. So along the skip connections, early results are concatenated with the later results. So we analyzed the memory usage of an image segmentation model on top of an existing tiny ML framework. So basically, to execute a model on the target system, two types of tensors have to be stored in memory. The first one is parameters, which are the weights of the model. Usually they are fixed after training. And the second one is activations, which are the intermediate results from the input data. So I measured the memory usage of parameters and activations for the segmentation model and a typical classification model. And here we found that even if the segmentation model has less number of parameters, actually it requires much more memory space for its activations. So that is, the segmentation is smaller than the classification model, but requires more memory. So this is why the segmentation model cannot run on the tiny embedded systems. So we investigated why the image segmentation models have such high peak memory usage and found two major optimization blockers. And then first one is large long-living tensors, and the second one is large interim tensors, especially used for concatenation. So the first optimization blocker is long-living tensors, which have this long lifetime along the skip connections of the network. So since the memory space cannot be shared when the tensors are alive, so these long-living tensors may contribute to the peak memory usage without being used for a long time. And the second optimization blocker is large interim tensor for concatenation at the end of these skip connections. So they usually need large memory space to concatenate two tensors into one tensor. So they may also increase the peak memory usage of the model, even though they are used only for a short time. So our main idea for overcoming the optimization blockers is dynamic tensor spilling. So in dynamic tensor spilling, long-living tensors are spilled into the local or remote storage before they become idle. And then they are fetched again from the local or remote storage before they are used again. So it can reduce the lifetime of the long-living tensors by spilling the tensor into the storage, and then also it can remove the large interim tensor by integrating the fetching process with the following operation. So to support the dynamic tensor spilling, we propose a new model optimizing framework called TinySeg. So this framework consists of a TinySeg model optimizer and TinySeg runtime. So this model optimizer takes a TensorFlow-like model as an input and interprets the model as a graph. And then it generates a memory plan for checking the peak memory usage. And then it analyzes the code range of the tensors. And then transform the graph based on the code range analysis results. And then it outputs the optimized TensorFlow-like model. And then the TinySeg runtime takes the optimized model and provides some custom operators and tensor transfer module that will implement the tensor spilling. So the code range analyzer analyzes the code range of each tensor, where the tensor is just stored in memory without being accessed. So it tracks the longest distance between def and use or use and use from the root of the graph. So based on this analysis result, the graph transformer selects the victim tensor to be spilled and transform the graph to insert corresponding operators. So the graph transformer first insert this spill operator to spill the tensors into the storage. And then it inserts the fetching operator to fetch the tensor from the storage at the end of the code range. So after the transformation, the lifetime of the victim tensor will shorten so that the memory space can be shared with other tensors. And after then, the graph transformer tries to fuse the fetching operator with the following operator, because if the fetching operator outputs the large interim tensor, then it tries to fuse the fetching operator to remove that large interim tensor. So the TinyStack runtime provides various optimizations to reduce the tensor spilling overhead and further optimize the memory usage. So the first optimization is bitmap-based tensor compression. So it is very simple compression scheme, which identifies the most frequent value in a tensor. In this example, it is -9, and then uses a bitmap to indicate the locations of the same value, so that it can avoid storing the same value multiple times. So it can reduce the size of the tensors to be spilled. And the second optimization is asynchronous block operation. So when the tensors are spilled into the local flash memory, the flash blocks have to be erased first to be written. So here, block erase takes much longer time than the read or write. So we propose to use another process core to hide the block erase latency via remote procedure call, so we can reduce the spilling overhead. And the third optimization is temporary tensor quantization, which is to quantize the temporary tensor used in the operators to reduce the peak memory usage. So for evaluation, we implemented our prototype framework on top of TensorFlow Lite for microcontrollers, and our implementation is available at our GitHub repository. And to test the image segmentation on top of tiny embedded systems, we created a tiny unit model which has 100,000 number of parameters. And then to measure the latency of the model, we used Arduino NiClaVision, which has dual ARM core, M7 and M4 cores, and with memory, 1 megabyte memory and internal and external flash memories. So we examined how the peak memory usage changed when we apply the proposed method step by step. And then after we apply the temporary tensor quantization, we could obtain 22% of memory size reduction. And then when we apply tensor splitting and fused fetching together, we could obtain the final memory reduction of 39%. So we also measured the end-to-end network latency with different spilling targets on Arduino NiClaVision. So the first option is to spill the tensors into the internal flash memory inside the microcontroller. And the second option is to spill the tensors into the external flash memory outside the microcontroller. And the third option is to send the tensor data to the remote host via serial communication. So even though the tensor splitting results in doubling the latency of the model, we successfully reduced the overhead of tensor splitting by tensor compression and asynchronous block erase. So at the end, we only got 6% of overhead to obtain the 40% of memory reduction. So let me conclude my talk. So Tiny Machine Learning aims to enable intelligent services with machine learning algorithms on tiny embedded systems with small size memory. So this work introduces a new model optimizing framework, which reduces the peak memory usage of a model with tensor splitting and fuse fetching. So with the evaluation results, we could show that the proposed framework can help deploy more intelligent models on tiny embedded systems. So thank you for your attention, and I would be happy to take any questions.
models. And can you explain briefly about the strategy you use? For example, which tensors are going to be spilled as a victim, or other kinds of strategies?
Okay. So to select the victim tensor, we first find the tensor that contribute to the peak memory usage of the model, and then select the tensor with the longest code range. That means the tensor is stored in the memory for a long time without being accessed. So that would be the victim tensor. So it repeats, repeats trying to spill the tensors until it reaches the target memory usage. Yeah, the details are already in the paper. Yeah, thank you.
Maybe two questions. First, so when you spill the tensor to the flash memories, did you consider the lifetime of the device? Because I think the flash memories of this controller has a limited lifetime.
Yes, that's a great question. So the number of block erases is limited in flash memory, but at the moment we don't consider the lifetime of flash blocks. So I think ideally we have to distribute the tensor data into different flash blocks, but yeah, at the moment, it is not implemented.
And another questions related to this, I'm a bit confused. So you say latency for remote cache is a lot faster than using internal flash and external flash memories?
Yeah, actually it was interesting to see how remote spilling is faster than the internal
because
spilling.
the remote is using the serial communication.
Yeah,
right?
we used the USB connection to transfer the tensor data to the host. So the USB connection was quite fast. And this for internal spilling, we have to endure the block erase latency. So if we hide the block erase overhead, then we could obtain much better results than remote spilling. But with the block erase overhead, the local and external spilling works.
Thank you so much.
Yeah, thank you.
Hello.
Okay. Thank you for the introduction. And hello, my name is Zejia Lin, and I'm from Sun Yat-sen University. Today, I'd like to introduce our work, MixPert, optimizing mixed precision floating point emulation on GPU tensor cores. This work was done with Aoyuan, Xianwei, and Yutong. Let me begin with some backgrounds. Today's GPUs and many domain-specific accelerators incorporate specialized architectures to accelerate matrix multiply accumulate, also known as MMA. This is an essential operation in many applications, and the NVIDIA's Tensor Core, AMD's Matrix Core, or the Google's TPU already incorporates such hardware to accelerate the matrix multiplication. And specifically, these operations are implemented as the hardware primitives. They issue one instruction on a tile of the matrix and compute the multiplication. So to use this hardware, we need to tile the matrix into fragments, and we load the fragments into the hardware and execute the multiplication of this tile in one instruction. So the tensor cores units are trading the precision for the performance, because the lower the precision is, the higher the precision. And from the GPU generations, and from different GPU generations, the low precision performance is also growing rapidly. And for example, the widely used TF32, FP16, BF16, or INT-A are supported on the Tensor Core units, and it also dominates in the deep learning applications. However, for many other general purpose, the common GPU applications, the need for the FP32 computation is still needed. However, such arithmetic is not supported in the Tensor Core units yet. And these units only supports the low precision, the mixed precision operations. So to bring the performance benefit of the Tensor Core units to accelerate the FP32 computation, we can emulate it using multiple low precision operations to correct the errors introduced in these low precision computations. For example, if we are to preserve the precision of the FP32 using the BF3016, which is introduced by Google, the BrainFloat 16, we may use 6 operations to emulate the computation from a software approach. However, for example, on the NVIDIA's A100 GPUs, the INT8 computation is much more faster than BF16, and if we can use, for example, 9 operations to emulate, we may obtain a higher speed up than using the BF16 to emulate. So previously, much of the emulation techniques are using the half precision types like the BF16, and we are exploring the use of the integer computation to emulate the floating point. And I'll give a concrete example on the previous emulation techniques. For example, to emulate an FP32 using the half precision, also known as the FP16, we may split the original number into 2 half precision numbers, and the first one preserve the higher parts of the mantissa, and the second one preserve the lower part of the mantissa. And because of the limited range and limited precision of the half precision, some of the bits in the range and the precision are discarded. So after splitting the number into 2, we may use the Tensor Core to compute them all in these low precision arithmetics. For example, the dark green multiplies by dark purple, and the dark green with light purple, and the light green dark purple. So it's 3 operations. However, to do such emulation, we need to scale and quantize them to the low precision one. And after the computation, we need to upscale and dequantize the numbers. So we may lose a lot. We may lose the precision in these steps. And also, there are many works using the like TF32 or BF16 for the emulation, and we observed that they degrade the precision like 540 times because of the error introduced in the quantization. So as previously mentioned, the integer components on the tensor core has much more faster performance than the floating point. And if we can control the emulation steps for using the integers for emulation, we may achieve much more faster speed up than the floating point. And the second question is how to control the error when we are using the fixed point for emulation. So we need to address 3 questions. We need to represent the floating point values into the fixed, using the fixed point to represent the floating point values, and we need to design a method to emulate the matrix multiplication using the fixed point. And we also need to balance the error and speed of the emulation. So for the representation, we are using 3 integers with the shared exponent bits to represent the floating point. I'll introduce it later. And we are using 6 to 9 emulation steps to correct the errors. Then these steps are tunable parameters. So if the application's error threshold is tolerate for larger errors, we may use less emulation steps, and we design a lightweight tuner to tune the number of emulation steps. So first is the representation. An FP32 number is represented as a sign bit, an exponent bit, and the 23 bits of the mantissa. So we can store the exponent in one integer, and the higher 20 bits of the mantissa into 3 integers, and the last 3 are discarded. So for the multiplication of the scalar values is very straightforward. It's very straightforward. For example, to multiply the x by y, and we may accumulate each the segments. We may multiply each of the segments of the numbers in pairs, and we accumulate them together. Then, because the tensor core units are executing the matrix multiply and accumulation in one step, so we also need to deal with the accumulation in the data representation, because the floating point numbers can have different the exponent bits to represent different range. So we need to shift the smaller ones to align with the the bigger numbers. So after the shifting, we can share the same exponent bits of the numbers, and then we can compute the mantissa parts of the multiplication. And after doing it, we shift them back to represent the original FP32 values. So For the applications may have many operators, we design a lightweight tuner to search for the area of different operators. We use a sampled input on the application, and we collect the time and area of the application, and we can adjust the emulation steps of the operators. And we evaluated on the NVIDIA 800 and RTX GPU and used the applications from Rodinia, and then previously works are from the linear algebra, genomics, and machine learning, and self-built benchmarks. So for a single matrix multiplication operations, we obtain 2.1 speed up and 1.2 speed up on RTX, and we preserve the error in a controlled manner. And for the application, in average, we have the speed up of 1.6 times, and specifically the HPL AI and the Sparkler. The HPL AI uses precision refinement steps, so we may use the less emulation steps to accelerate. And also the Sparkler is a genomics comparison algorithm, and we can also use less precision for the commutation. So the tuner detects it and uses less emulation steps to gain higher speed up. So in conclusion, we identified the imbalanced performance and precision trade-off on the previously emulation techniques, and we designed and emulation methods on the integer tensor cores and obtained 1.6 to 2.1 times speed up with controlled error. Thank you.
Okay, thanks. I think we are running out of time on this one, so we have time for just one question. If there is, or we can go to the next talk.
Okay, thank you.
Thank you. Next talk is by Kyung-Woo Lee. He's working at Meta since 2019 in the programming and language runtime team. He's interested in compilers, runtimes, and currently working on releasing mobile apps.
Hi everyone, I'm Kyung-Woo. I'm software engineer working at here at Meta. I work with Maman and Alice for this project. Today I'll be talking about our work on optimistic and scalable global function merging. The size of mobile apps keeps growing as we keep adding new features. The graph shows how quickly the app size has increased over the past year. Compared to the blue line on the top, take a look at the green line on the bottom. That shows it's growing relatively slowly. That's where size optimization come into play. Today, I'll be focusing on two main strategies for size optimization: function outlining and function merging. A function outliner finds repetitive code sequences and replaces them with function calls to a shared function. I focus on machine function outliner in this talk. We replace this, basically, it replaces the same machine instruction sequences by native function calls, so the call overhead tends to be low. So it can effectively reduce code size. Here's the example with the two functions. The code sequence in green, they are identical. If I outline them with a native function call, they will look like this. resulting in only 7 instructions on the right-hand side, as opposed to 8 instructions originally. Function merger works on entire function rather than specific code sequences, unlike the function outliner. A function merger also can handle similar functions by parameterizing differences. Function merger is implemented at the IL level, so the core overhead tends to be high because it needs to abide by calling convention. In this example, 2 functions, they look very similar to each other, except the core target constant, f1, f2. We may come up with a shared merge function with the additional parameter here, x2. The original 2 functions become the thunks while providing their individual context through this parameter. As you can imagine, for both function outliner or merger depends on entire intermediate representation called IR. They need to be explicitly compared in order to find same or similar instruction pattern across the entire app. This can be computationally intensive. However, our approach is based on using summaries that are applicable to separate or parallel compilations like ThinLTO. So we have developed optimistic global function merging that utilizes these summaries to track the function similarities. Our technique optimistically create merging instances, and then they are folded by linkers identical code folding called ICF. In our comprehensive cogeneration framework, we've seamlessly integrated the global function merger and global function outliner into single framework. We also provide a single cogeneration framework that are applicable to distributed build environment. Our impacts on real-world mobile apps are substantial. I will get into detail in the later slides. Let's break down ThinLTO with the global function outliner that has been published before. The key idea is to repeat cogenerations to get the sum global view. Basically, during the first cogen round, we performed outliner locally to find some local outline instances and then publish such opportunity into sort of global summary named global prefix tree. During the second cogen round, we identify cross-module candidate, and then we create those instances. And finally, link time, if these two outline instances are truly identical, we can fold them through linkers ICF. Let me give you a more concrete example. Let's say you have 2 functions in the module 1, another function in module 2. They look very similar. The code sequence in green are identical. We can replace them by some function, outline function like this. However, the function in module 2, they cannot be outlined because it's singleton. There is no match within it. Once we have outline function, we compute the stable hash sequences that corresponding to machine instruction in outline function. We can publish into global prefix tree. This is merely compact representation of tracking hash sequences using traditional triad structure so that we can share the common prefix to save size in summaries. During the second cogen, with the same input, we can apply local outline same as first step. But now, because now we have a global prefix tree, we are now able to outline another instance in module 2. Please note that the outline function has unique name for safety because there may be chance of hash collisions. At the end, during the link time, if these 2 outline functions turn out to be identical, we are able to fold them safely. So now let's explore how global function merger is integrated into this system. Function merger was implemented at IL level. We need to push it down to pre-cogeneration hook first. Likewise, we need to repeat cogenerations. During the first cogen, we analyzed functions to create some stable function summary and then combine it into global summary. During the second cogen, likewise, we create merging instances optimistically and so on. Let me give you a more concrete example. Similarly, they look very similar, except core target constants are different. At this step, we just compute summary, which are independent of intermediate representation, as you see. It consists of function hash, which is based on contents of functions, except the core and the constant targets. So as you see, the hash are all identical. We have a different name in string. We keep track of constant location that is represented by a pair of instruction operand, instruction index, or operand index, etc. We can publish it into some global merging information where stable function summary are grouped by same stable hash functions. And then we can compute the parameters. That is the minimal set of constant location that vary across different stable functions. Now let's apply the second step with the same input. Now we are able to compare IR against the global summary that we just previously computed. As you see, now we create merging instances in module 1 and module 2 independently. Likewise, global outliner case, we create merging functions uniquely with unique name for safety. At link time, if they turn out to be same, we can merge them like this. So let me share some data on the size saving achieved by applying both function merger and function outliner. This graph compares several function merging techniques alongside with the global function outliner. The global function outliner alone contribute code size reduction of 70%, which is significant. In contrast, the built-in default function merger or the LFM, which is local function merger, adapted from Swift function merger, result in only marginal size impact. However, our global function merger significantly improves the F size, around 3.5% in addition. I mentioned that earlier, our approach is based on repeating code generations. Repeating code generation, of course, increases build time, which is not good. More importantly, it may not be suitable for distributed build environment because we have additional synchronization point between two code generations. So we split them into two distinct pipelines. One is writer on the left-hand side, the other is reader on the right-hand side. Basically, former produces cogen artifacts that represent outlining or merging opportunity, while the latter, the reader, simply reads the artifacts and applies optimization in separate. We can also apply this framework into continuous integration environment, where target source code also can evolve. Basically, we can produce cogen artifacts infrequently on the left-hand side. The actual optimization build on the right-hand side can consume these artifacts and apply optimization safely. As you can imagine, there may be mismatch between the writer and the reader. So we may have a stale summary that can negatively impact the app size. So we tracked the app size regressions over the last 3 weeks, refreshing cogen artifacts weekly. Take a look at the red line on the bottom, which is the case with outline only, which works pretty well, good well. The size of head is less than 0.2%, even though we have hundreds or 1,000 commits in daily daily commits in our report. But if you look at the blue line, when we combine merger and the outliner, it can spike up to 0.7%, right before the causal effect update on the purple line. This graph shows comparison of build end-to-end build time that includes compilation and linking and everything else. The single core-gen pipeline is about 9% faster than double core-gen approach. In fact, if we compare just link time only, the difference is even larger. It's like about 70%. Depending on machine configuration and build environment, the size and the gap will be even larger. As you can see, adding the global function merger on top of the global function outliner, the build time impact is very negligible, no matter whether you use a single core-gen or double core-gen approach. So to conclude, I've demonstrated the effectiveness of our global merge function and also global function outliner that can significantly save app size by up to 20% when combined. I've also shown that our cross-module transformations can be applicable to separate compilation environment. Last but not least, finally, we've gotten legal approval. So we have begun upstreaming all this code, starting with the global function outliner. This includes code generation framework that I just described, and the tools that can deal with the stable summaries offline. Please check out this link for our RFC and the PRs in LLVM, and follow our contributions. Thank you for your attention. I'm ready to take any questions you might have.
Hello. I have a question. So how does this play well? Like, how does this play with the inliner? Because you're adding with the inliner.
I didn't hear that very well.
With the inliner pass, does it work well with that?
I didn't hear the last Q.
Last question is, because you're doing function outlining,
yeah.
How does it work with the function inlining?
Function inlining typically happens only in the compiler pipeline. As I explained, the function outliner or function merge happens very late pass. So it's kind of sort of orthogonal, although it could be related. But normally the compilation flag that we apply for our mobile apps are under minimum size optimization, say OZ. I don't know whether you're familiar with that. In that case, inlining is mostly prohibited.
Okay, thank you.
Okay.
Thank you for the nice talk. So these techniques are for reducing the size of code, right?
Yes.
But I wonder how it affects the branch prediction performance.
Oh yes. Yeah. So basically, your question is about the impact on the performance, right? So as you can imagine, it increases more function cores. So it may impact the performance in CPU or cache performance for sure. We actually have there's two things I can explain. Mobile apps are not really bound to CPU. So size is actually more important than anything else. Because the smaller means actually the faster to start up, because startup performance is bounded by the memory page fault rather than cache performance. And also, so of course, there's a cases where we do care about performance, like scroll performance or sending message in the Messenger app. Then we do care about performance. In that case, we have a PGO. So I didn't cover that in this talk. So we have a proprietary PGO technology. We also actually upstream the lightweight instrumentation that is compatible IR-PGO in LLVM. We actually upstream that. So I'm happy to talk about offline. So if you're interested, yes.
Okay, thanks.
Okay.
Okay, so our last one before lunch is by Daniel Bybert. He's a master's student at TU Dortmund, and he's about to start his PhD at TU Dortmund. And his research interests are on memory-based optimization, specifically on tree-based.
Oh, that is not,
look right.
no. Try mine.
Yes. Is this one? Okay. Hi, I'm Daniel Biebert, and today I want to talk a bit about language-based deployment optimization for random forests. So first off, a quick introduction what decision trees and random forests are for those who don't know. Decision trees are a form of inference where you have a feature vector, so some values describing some object, and you want to find out what its class is probably going to be. The way a decision tree does that is it takes the feature vector and repeatedly compares it to some split value. Depending on the outcome of the comparison, either the left or the right child is then taken, and this is done recursively until a leaf node is reached where a prediction is made about the class of the object. Random forests are just a collection of multiple trees where the predictions are then combined. One very performant and popular way of implementing a decision tree is as an if-else tree. In an if-else tree, the structure of the tree itself is encoded as if-else blocks. So the comparison of each node is written in the condition of the if statement, and then the whole left subtree is written in the if part, and the whole right subtree is written in the else part. For the optimizations we want to do, we need two things. We want to have as much hardware control as possible, but also be as hardware independent as possible. For that, we chose LLVM-IR as our target language. And this also implements an if-else tree. It should be said that this isn't completely correct LLVM code. I condensed it a bit for more readability. But this still implements the same if-else tree functionality, with first doing the comparison and then conditionally branching to either the left or the right child. One last interesting and useful characteristic of a decision tree is that we can extract a probabilistic model. During training, we know how many samples will fall under the left or the right child for each node. And with that, we can calculate the probability of the left or right child to be taken. With those probabilities, we can then calculate the absolute probability for each individual node to be used. So for example, this leaf node will have a 45% chance of being accessed during one inference run. Okay, so much to the background. Let's look at some actual optimization ideas. First off, we want to use all the CPU registers. As an if-else tree implementation is not as complex as other implementations, most of the registers of the CPU will probably remain unused. We want to use all of those to potentially reduce the number of memory accesses. In the search for something to actually put in those registers, we can see that the feature value at index 5 is used both in the root of the tree and in the right child. So by placing this value in a register, we can reuse it without having to load it from memory. And that's exactly what we do. Replace the value in a variable, and this suggests to the compiler to place this variable in a register. And this eliminates, in this instance, one memory access and therefore improves performance. This can, of course, also be done for multiple feature values. So, for example, if we imagine a way bigger tree where the feature value at index 2 is also accessed multiple times, we can also place it in a register. And crucially, this also works for random forests. Because if we, the same feature vector will be used across different trees. Therefore, it can be useful to also reuse the same values inside registers. However, here it should be said that this is only possible if the trees are implemented in the same scope, so in the same function, as to not discard the contents of the register. Another way we can improve performance is by branch reordering. In the current implementation, if the comparison in a node is true, then we take the left child, which is branchless because the code is written directly underneath the code for the parent. However, if we take the right child, we branch, and therefore, we branch. However, in this instance, we can see that only 25% we do not branch, which is bad, because usually we don't want to branch to not have things like pipeline flushes. So the idea here is to swap these two trees. This can be done fairly straightforward. On the one hand, we have to simply swap the code for these two subtrees. And on the other hand, we also have to update the comparison in the root of the tree. Before it was a greater or equal, and now it's a less than. This is done to ensure that we still get the same prediction result. So when the structure of the tree has changed, the result will not have changed. Another way we can reduce overall branches is to use predication. Predication is a method where you compute multiple options at the same time and then only conditionally retain one of the options. So in our example, usually we would here branch to either the left or the right child. However, we can use the select function. This conditionally only retains one of these values depending on the comparison outcome, and we can then return that. This can also be done for larger subtrees, so we can add more comparisons and more select functions to conditionally only retain one of the prediction. Of course, at some point, this will result in too much computation for the benefit of less branches. Therefore, there's a certain trade-off of how large of a subtree we want to predicate and how much benefit less branches will give us. To find a threshold for when we want to start using predication, we can use the probability of the nodes. How to find such a threshold, I will talk about a bit later. One last method of optimization is to change the way we do the comparison in general. So often the type of both the feature vector and the split values is a floating point number. However, floating point comparisons can be more costly than integer comparisons due to reasons like the floating point unit just needing longer or having to copy values from into a floating point register. Therefore, if you could just use integer comparisons, this would speed up the whole process. However, this cannot always be easily done, because if we just use things like casting the floating point value to an integer, that would lose some prediction value because there's some loss of information and maybe there's another prediction will come out and we lose some accuracy. Luckily, we can still use integer comparisons for this. Rather than casting the floating point value to an integer, we can simply interpret the bit vector that represents the floating point value as a 2 complement integer value. So no change is actually done, we just interpret the bit vector differently. With this, we can still use the integer comparison and get the correct result. Some care has to be taken for this, because depending on the sign of the numbers, the comparison used has to be changed. However, all of this can be done pre-compile time, so no further overhead is introduced during runtime. Okay, so we have these different methods of optimization. Now I want to quickly point out how we can find thresholds and optimize it further. So we have our LLVM IR code. And we can then statically compile and link that to some test environment we have compiled previously. We can then profile that using PAPI, and this gives us information how well our optimization worked. We can then use this information to adjust our thresholds. So for example, how many registers to use or when to start predication, and then generate new code. This can be done in a loop to find the best thresholds. Yes, thank you very much. I hope I could give some insight of how random forest might be optimized.
Any questions before you become too hungry?
Thank you for an intriguing talk. I wonder you have some motivational experimental results. For example, the LLVM alone, does it produce quite efficient code for random forest?
Not for the LLVM part. So we have implemented some of the methods shown on a more hardware near level. So for example, the register stuff in assembly. But all of the combining that in LLVM, that's still work in progress. So we don't have concrete numbers for that yet.
Okay. Looks like everybody is not asking questions because they want to go in. Okay. Thank you for the talk. And let's go for lunch. And we reconvene at 13:40.
Hello, I'm happy to present our work. I'm Ki-young Jung from Yonsei University, South Korea. And here are my co-authors. Our work is orchestrating mixed precision models on a shared precision scale level MPU. The title is self-explanatory. This is our target application, this is our target hardware, and this is what it did. I will tell you briefly about the target application and hardware. To improve inference latency while minimizing accuracy loss, we often quantize layers with different precision depending on their effect. The mixed precision model looks like the example, which has multiple layers with different precision levels. Our target architecture is the Precision Scalable MPU, or PSMPU. Here is a conceptual illustration of the PSMPU. Each processing element, PE, is made up of multiple small microprocessing elements called micro-PEs. When 4 micro-PEs are working, they can process a 16-bit operation in this example. When 2 micro-PEs are working, they can process an 8-bit operation. In the case of 4-bit operation, it is sufficient to use only 1 micro-PE. An insight here is that we can run several mixed precision models on a PSMPUs concurrently instead of running one model and conditionally turning off the rest of the micro-PEs depending on the precision level. Here are the real examples. This is the result of processing multiple mixed precision models, VGG 11, 13, 16, and 19. Each rectangle represents an operation of the models. The width is the number of precision bits, and the height is the processing cycle time. We ran the models in a round-robin manner, one from 11, one from 13, one from 16 and 19, and again 11, and so on. By doing so, as a result, there are a lot of empty spaces in the figure, meaning that some of PSMPU's micro-PEs are not being used. This is a manually optimized version. As you can see, the rectangles are well scheduled with little space between them. Compared to the round robin, there is 25% performance gain in this way. PSMPU's performance relies heavily on the scheduling capabilities of mixed precision models, meaning that it is not an easy problem. Then what makes it difficult? First, we must consider the variance in cycle times between operations. The gray rectangle represents the underutilized times of the PSMPU. As can be seen in these 2 examples, we need to group operations with similar cycle times. Here, A1 is not a good group, while A2 is a good group. Second, the greedy approach often fails. See figure B1 at the beginning, running blue operation and purple operation together to utilize the full micro-PEs of the PSMPU is not a good idea because 2 high latency operations, green and purple, are processed separately, increasing the overall processing time. In this case, as shown in figure B2, running blue alone, processing green and purple together, and red alone will give you better performance. Based on this insight, we propose an efficient and effective dynamic programming-based scheduling algorithm on a PSMPU. This is an overview of scheduling process. First, make mixed precision models using the Hawk library. The generated models are profiled on a PSMPU to obtain a required cycle time for each operation. And then scheduling mixed precision models on a PSMPU. This is the main contribution of this work. Finally, we can run it on a PSMPU according to the provided schedule. Back to the main contribution of our work, it consists of 2 steps. Step 1, pre-processing. Let's assume that we have 4 DNM model graphs where each node contains the precision bit and the number of cycles. To combine all the models, this step creates two virtual nodes and merges the graphs into a single graph for the next step. In step 2, We are going to form sequentially executing groups by partitioning graphs. Operations in the same group are processed together on a PSMPU. Let's create the schedule. First, this is trivial that the end node forms a group by itself. And main question is, how do we form a next group? For this question, we propose a recurrence relation. Here are the details of the DP expression, but I don't think it's easy to follow now. So to put it simply, this is a top-down manner DP algorithm that constructs a group of leaf nodes from the back of the entire graph. It is like recursively cutting leaves by considering the optimality. Following the DP expression, all possible candidates that can form a group together are iteratively selected. The rest of the graph, colored in red, is computed and finally obtains the optimal schedule candidate through the DP. We can select another candidate. This is also another. And even we select just a single operation for group formation. Considering recursively these possible candidates gives you an optimal schedule like this. This is the result of VGG 11, 13, 16, and 19. Let's take a look. You can easily find that it is well stacked again. So far, it looks good, but I think we can still do better regarding the scheduling such time. Think about these two models. Is it a good choice to form a group like the yellow one? I think not, because the green ones and blue ones are not able to make groups because of the dependencies of the yellow group, so the greens and the blues must be processed one by one. The yellow group will not be in the optimal schedule, therefore we can prune this case. To consider these cases, we introduce the process rate R. The process rate R means the relative position of each node with respect to height, which is calculated like this. It's a real number between 0 and 1, representing the height in a chain. By iterating all the chains, we can get process rate for all the operations. It looks like this. Then how can we decide the threshold? For example, 0.4 as a threshold. We try to form a yellow group of whose process rate is 0.5, 0.6, 0.8 respectively. The maximum is 0.8, while the minimum is 0.5. The difference between them is just 0.3, which is less than the threshold. As this is a valid candidate group, we can take it into account while scheduling. However, in this same group where the threshold is 0.2, the difference between them is greater than the threshold, which means that this candidate is not valid. Therefore, we prune this case. Combining the DP and the process rate together, it is expressed simply like this. This is how our algorithm works. We had evaluated the proposed scheduling algorithm on this system. We used the Hawk library to make mixed precision models, MLIR to schedule the operation of the models, and PSMPU to obtain a cycle of great information as follows. We used these 4 baselines to prove the effectiveness of DP and DP with process rate. Serial execution is the worst execution scenario, while the theoretical minimum is the lower bound or the ideal case. Round robin selects node alternately, and this scheduling selects the highest node in the graph. We experimented with the scheduling algorithms on 12 data sets generated from Hawk. Let's see the data set 1. The graph is normalized by the serial execution. The dotted line is a theoretical minimum, Tm. We can see that round robin or list scheduling is far from the Tm, the 37 percentage point gap implying the better scheduler. That is our DP-based scheduler. DP is much closer to the dotted line, meaning that it is much better than other baselines. See average performance. DP is above RR and RS, showing more than the 20% performance improvement. This shows the trade-offs of DP when considering the process rate. The x-axis, the relative search time, and the y-axis is the relative performance. Both are normalized to a threshold of 1.0. The upper left corner is the best, meaning that you get the best performance at a search time of 0. Each dataset is plotted as a function of threshold. As shown in this graph, smaller threshold go to the lower left, and the larger threshold go to the upper right. We have observed that the performance of the threshold value becomes saturated after 0.14. In conclusion, we reveal the existence of underlying potential within a shared PSMPU, which has been hidden due to the lack of appropriate scheduling algorithms. We propose an efficient scheduling algorithm based on dynamic programming to extract the best performance improvement of PSMPUs. Thank you for your listening.
Okay, questions? If no,
okay. Take a breath. And do you think your approach could scale to GPUs?
Actually, I didn't think about that, but my algorithm can work at a high level, so I think it works on GPU.
You did not mention about the optimality of your dynamic programming. Is that optimal?
Yes, it's always optimal, but if we consider DP with process rate R, becomes suboptimal.
Okay. So it's optimal under the condition that you have basically sequential flow of that. So if you also consider the precision assignment, how do you do that?
We didn't care about that because we just used mixed precision models generated from the Hawk library, so we didn't care about that.
Is that the next step you are doing? You are interested? Or?
Actually, I'm interested at another one.
Okay. Thanks a lot. Okay. If no further questions, let's thank the speaker. Okay, let's try again.
Yes.
The second speaker will be Guanyu Chen from Zhejiang University.
Okay. Guanyu, can you hear me?
Yeah.
Okay, great. All right. So I'll let the chair talk to you.
Okay, good. Guan Yu, you can start. You have 12 minutes for a talk.
Yeah. Okay. Good afternoon, everyone. I'm Guan Yu Chen. I'm delighted to present our recent work. The system is
Wait a
advisor.
second. We don't have your sound. Give us some seconds.
Oh, okay.
Can you try? Guan Yu, can you try to say a few words? Do you hear me?
Oh, yeah.
Yes. So I can first share my experience. So I organized a virtual event in 2020. Was the easiest one. It's only virtual. Then first event was hybrid in 2021. Was easy because we do not talk in person. So, but we only watch the TV there, like a public viewing. It was also easy. The third one, we had a hybrid event that we talk in person and broadcast that outside. It was also easy because you don't have to worry anything else. And it started to become more complicated. Then you have the hybrid event, you have the panel members in person, some panel members online, and then you start to have all the disaster organizations. And then it became more and more complicated nowadays. Can you say some words, Guan Yu? Not very clear. Can you just continue saying something? Just start with something or sing a song.
1, 2, 3, 4, 5, 6.
Yeah, it's 1, 2, 3, 4, 5, but we cannot hear that.
Can you speak louder? Just try your best. So you're speaking to someone.
Can you speak louder, as loud as you can, and let's see what happens.
1, 2, 3, 4. Oh, it's so loud. And
Where's the output? I'm a bit lost. Where's the audio output?
Where's the audio?
I'm a bit confused. Is it just the laptop? Can you try again? What is 3 plus 3?
3 plus 3?
Yes? Now let's go ahead. Yes, please. The stage is yours.
Oh, I start?
Yes, please.
Okay. Good afternoon, everyone. I'm Guan Yu Chen. Oh, okay. And I'm delighted to present our recent work. The system is called SmartVisor, a user-friendly hypervisor for mobile robots. I will take you through the key points of our research. Currently, the execution of robot tasks relies heavily on the support of operating systems. Deep learning, SLAM, and entertainment applications require the support of Linux, while RTOS is needed for hardware control. However, most existing operating systems struggle to support such different features at the same time. Linux lacks real-time capabilities, and RTOS is limited in its system functionality. Virtualization is a viable solution. Nowadays, most of hardware supports virtualization features. For example, the ARM architecture introduced exception levels to support virtualization. Considering these factors, we designed SmartVisor, a virtualization software platform for mobile robots. We list several mainstream hypervisors and classified their implementation architectures into monolithic kernels, microkernels, and standalone system software. For instance, PVM is a hypervisor developed based on Linux, while BAL is a standalone hypervisor. It can be observed that hypervisors based on microkernels are still rare. However, microkernels provide strong isolation and basic system functionality, making them a balanced and ideal choice for hypervisor implementation. The trend in designing robot systems has shifted towards adopting mixed criticality systems, which utilize multiple kernels to execute tasks with different criticality levels. The MCS refers to the integration of computer hardware and software capable of executing applications with varying criticality levels. Considering the significant costs associated with development and maintenance, virtualization is a good way to construct multi-operating system environments. The hypervisor ensures partitioning and isolation of each operating system. In our work, we also considered the requirements of MCS and designed SmartVisor to meet these needs. With SmartVisor, we can manage multiple operating systems and ensure their appropriate partitioning and isolation. Our goal is to provide a user-friendly hypervisor platform for mobile robots that supports the execution of applications with different criticality levels. During the deployment of the hypervisor on actual robots, we encountered several challenges. Slow boot speed, difficulty in updating the system, and low reliability were common issues we faced. To make SmartVisor more user-friendly, we developed a virtual machine management module to address these challenges. The architecture diagram of SmartVisor illustrates the various modules designed to support the operation of multiple virtual machines. The multi-VM support module enables efficient collaboration between virtual machines. The driver support module provides service to the VM management module, and the VM management module manages the state of virtual machines. To tackle the startup issue, we implemented a partial init scheme by prioritizing components with fast startup, such as the RTOS, and utilizing page allocators to meet the demands of large pages in Linux. We significantly reduced SmartVisor's startup time compared to the original SEL4 system. In terms of file loading, we incorporated local file reading and remote file downloading capabilities into SmartVisor, enabling different access to the image files. For monitoring, we proposed a hybrid core monitoring scheme, where the small core monitors the large one. Additionally, we implemented a backup system to ensure recovery in case of failure. The state transition diagram for recovery shows that the backup system can be activated regardless of the success or failure of the recovery process, providing essential service support. Moving on to the experiments, we conducted system experiments on the RoboKit using the NVIDIA Jetson NX. SmartVisor will run a guest Linux and a guest RTOS at the same time. To evaluate virtualization performance, we compared the benchmark scores of bare metal Linux and guest Linux using Unix Bench. The results indicated that the SmartVisor incurs approximately 30% virtualization overhead. Additionally, we observed that the allocation of 2 MB pages has a more significant impact on system performance than 4 KB pages. We examined the system's boot overhead by comparing the optimized system with the original SEL4 hypervisor. We observed a significant reduction in startup time, except for the initialization of the SEL4 kernel. The optimized guest Linux startup time was measured at 17.9 seconds, while the RTOS startup time was 14.3 seconds. Furthermore, we conducted experiments in which the RoboKit running SmartVisor was deployed in an underground garage. The resulting point cloud map shows the robot's fundamental capabilities. To test the system's recovery capability, we intentionally caused a crash in the guest Linux. The SmartVisor will detect the issue and initiate the recovery process, as demonstrated in the accompanying animation. SmartVisor successfully recovered from the crash, resuming normal operation within 30 seconds. In conclusion, our work presents SmartVisor, a user-friendly hypervisor platform based on a microkernel architecture for mobile robots. We addressed the challenges related to slow startup, difficulty in updating, and low reliability through the design of the virtual machine management module. We successfully deployed SmartVisor on a mobile robot and thoroughly tested its core functionalities. Thank you all for your attention and patience. If you have any questions, please feel free to ask.
Okay, thanks. Any question? Also, I have one. So it seems that your SmartVisor is not limited to mobile robots. Right? So what is the reason that is limited to mobile robots in your study?
Sorry?
So the title mentions that this is for mobile robots, right? The SmartVisor. Yeah. But in fact, it's a general solution. Am I right? Not only limited for mobile robots. Especially you did not actually have special considerations about robotics in the hypervisor part. Or did I miss anything? What is the limitation that, what do you actually limit the scope to mobile robots?
When we deploy the, first we use the hypervisor and deployed it on the mobile robots, but we meet some issues such as boot slowly, to update, and low reliability. So we optimize the original hypervisor and make it and design the SmartVisor.
Do we have further questions?
Some modules.
Sorry, do we have further questions? If not, then the same speaker. So thanks. Go on. Let's move to the next talk. Okay. So next talk is going to be given by Philipp Rafek, who is a PhD student from University of Erlangen, Nuremberg, in Germany. Sorry. Oops. Let's take it back. Fault tolerance. I have another one. Let's not destroy this. Okay. So he's a PhD student from Erlangen in Germany. So today he's going to talk about Waka with cooperators also from Erlangen. The stage is yours, please.
Oh, thank you.
Microphone is muted.
Okay, so now it's working? Yes. Okay. Well, thank you. I will present WOCA, our approach for avoiding intermittent execution in embedded systems by worst-case analyses with device states. And we'll first have a look at the systems we target, which are device-bound energy-constrained systems, such as this solar-powered Bluetooth-connected smartwatch, for example. And these systems have two characteristics. First, they harvest the energy from the environment through various means. And second, they need devices to fulfill their functions and perform properly. So they usually have an embedded microcontroller, which controls a lot of other devices, such as sensors for collecting information from the environment, or transceivers for wireless communications. And in these systems, we face a couple of challenges. We have an unreliable energy source, so energy is a scarce resource that we cannot waste. And we have frequent device use with a varying power demand, depending on which devices are currently used and in which state these devices are, and so on. Considering the unreliability of the energy source, we will eventually face intermittent execution. So although we have some energy buffer, if the input power is sufficiently low for a sufficiently long amount of time, the system energy will drop below the operational threshold and we will face a power outage. What we want to do is maintain the consistency of the system throughout those power outages and resume operation as soon as sufficient energy is available again. For this, we will have some form of system checkpointing. The problem with existing checkpointing approaches is that they have to potentially re-execute device operations because we just cannot transmit half of a packet and then wait until energy is available again and then finish with the second half. This is just not how these device operations work. So we see, for one, these consistency mechanisms come with an energy overhead, and the potential re-execution simply wastes energy, which we want to avoid because energy is a scarce resource. Coming from the hardware to the software part and looking at an example task, here a task that just transmits a packet, we see that we have some configuration parameters in the device operations, and these configuration parameters potentially determine the power demand of the device. So if we want to know how much power a device operation needs, so we can work around power outages, we have to keep track of all these device configuration parameters, which can be can happen anywhere in our system. So we cannot only look at tasks in isolation. We can, for example, also have interrupts in our systems. These interrupts can also, again, itself use devices, like a sensor device in this example. But what's important is that the influence of an interrupt on the system can go beyond its own device use. In this example system, it matters for if the interrupt occurs before the other task is using the device or when the other task is currently using the communication device. On the right-hand side, the energy demand of the system, indicated by the orange area, is significantly increased. So we see that also the system context determines the power demand. We've seen a lot of problems until now, so let's recap them shortly. We have the problem of device states with a varying power demand. We have a problem of asynchronous device use in different contexts in the system, including interrupts. And we have the problem of re-execution due to transactional device semantics that we want to avoid to not waste energy. So what we want to achieve is we want to guarantee forward progress of the system, we want to guarantee consistency of the system, and we want to make efficient use of the energy we have available. In the following, I'll present an overview of our approach, present some evaluation results, and conclude the talk. And I'll start with our approach. VOCA stands for worst case analysis. So what we'll mainly deal with is to how we can statically capture device behavior and system behavior. For the device behavior, we introduce device graphs, which contain all possible device states, the maximum power consumption of each device state, a possible transition between states, and also internal device configuration states, which could be, for example, the output power of a transmission, the bandwidth of a transmission, and lots of other configurable stuff. Once we have such a device graph for every device in our system, we can again have a look at the system software, and we can identify device state changes on all possible system paths and decompose the system into states with a constant power consumption. So for this example task, for a package transmission, we can identify device operations in the code and divide the task into different sections and construct system graph nodes corresponding to these sections. And each of these nodes has a distinct but constant power consumption. And with that, we can also handle interrupts by just checking which interrupts can occur in which node, and then in a context-sensitive manner determine with which power consumption the interrupt will be handled. And so we can address the issues with interrupts we have seen beforehand. And once we have constructed our device graphs and constructed, with the help of device graphs, our system graphs, we can then convert the system graph into a mathematical optimization problem, in this case, the integer linear program. And we can solve this problem with established techniques. And with this, we can find the whole system worst case energy consumption of the task in our system. We can dimension our energy storage accordingly, so we have a meaningful amount of energy to perform meaningful work. And we can start task only if we know that sufficient energy is available to actually finish the task. And with this, we achieve guaranteed transactional execution semantics. We also implemented this approach. We modified the Clang to take as input the source code, which is potentially annotated with some flow fact information, such as maximum loop bounds and the device graphs. And the Clang then outputs the system graph, the control flow information, such as loop bounds, and the final executable. And we also modified the analysis tool Platin to take as input the system graph, the control flow information, and the executable, and output the aforementioned worst case energy consumption bounds. That was a quick overlook of our approach, and I will now present some evaluation results. We'll first have a look at the benchmarks we will see. We have a purely computational benchmark that doesn't use any devices. We have a rather simple device use, namely a temperature sensor readout, and the use of a more complex device, namely a LoRa transmission. And we have this LoRa transmission benchmark also in 3 variants, which have varying parameters for the payload, the bandwidth, and the spreading factor. So we have a context-sensitive device use in these benchmarks. We also have an application benchmark, which comprises a sensing phase, a computation phase, and an actuation phase, where actuation is, again, the LoRa transmission. And we also have 2 further variants of these application benchmark, where an interrupt can occur with a low or a high frequency. For the approaches we will compare, we have, of course, our approach, WOCA. We have an approach that is not aware of any context of the device usages. We have another approach that is device agnostic, so it has to assume that all devices are always on all the time, hence the name all on. And finally, we compare against a chip-based approach, which doesn't care about static analysis, but just checkpoints when an energy interrupt signals that the energy is low, and before each device use, so we don't have a checkpoint in between device transaction. To not only evaluate our analysis, but also have some actual runtime results, we also designed our own evaluation platform that we use for the evaluations. And in the following, I will present 2 evaluation results, one for the analysis and one as a runtime result. There are many more results in the paper, but for timing constraints, we will just have a look at 2. And as I said, we will first look at the analysis. We see here the energy bound from the device agnostic, the context agnostic approach, our approach WOCA, all normalized against the worst observed energy consumption. And we see that while there is some degree of pessimism, our approach WOCA yields significantly lower results than both the all-on device agnostic approach and the context agnostic approach. So we see the context awareness of WOCA and the modeling of internal device states and keeping track of device configuration parameters reduces the pessimism of the analysis results. And for a runtime result, we see here the recorded runtime for 100 executions for each benchmark on an intermittent power consumption. And what we first see is an outlier for the temp benchmark for the JIT-based approach. Because the temp benchmark is rather simple and the JIT-based approach takes a checkpoint before each device use, the overhead of taking the checkpoint really comes into play here for such a simple benchmark. But also for the more complex benchmarks, SEND, SCA, and the interrupt variants, we see that the WOCA in green yields better results than both the device-agnostic approach and the JIT-based approach. We also see another effect of the reduced pessimism of the WOCA bounds as for the low-frequency interrupt variant for the SCA benchmark. We see that the device-agnostic research bound is actually infeasible to safely execute the benchmark for our target platform and the chosen energy storage. So we see that WOCA does not waste energy for avoidable re-execution, and that the tighter bounds of the analysis of WOCA increases the number of feasible systems. With that, I'm at the end of my talk. We've seen 3 problems at the beginning, and we can handle device states by modeling devices in the device graph. We can handle the asynchronous device use by context-aware modeling of device usage in the system graph. And we can avoid re-execution by transactional guarantees that we have through our analysis bounds. The WOCA's hardware and software is publicly available. And with that, I thank you for your attention, and I'm happy to answer any questions.
Questions?
So thank you for the insightful presentation. I'm a little bit curious about, in your evaluation, you use the execution time as the metrics, right? So what?
No, for this result, you mean, right?
Yeah. Yeah. So what is the real world impact to the energy, like power profiling or?
First of all, we use the runtime here because it's just an easy to employ metric to measure indirectly how well the approach performs, because the more power outages an approach encounters, the more checkpointing it has to do, the more restoration it has to do, the longer the runtime takes to execute the same benchmarks, the same amount of time for the same available energy. So that's why we used it here. Does this answer your question, or was there a second part to it that I missed?
Yeah, I'm just a little bit curious about, we can obviously find there are big difference between the WOCA and other approach on the runtime performance. But let's say, could you give an example, like if we produce a simulation experiment, how much energy would be reduced? Like any sensor or any chipset?
Yeah. That is actually highly dependent on how much energy you can harvest. It really depends on the concrete scenario, on how good or how bad your harvesting conditions are. Actually, I have some other results which showcase this a bit. These are very high frequent power ons and power offs, so in the microsecond range. And we see that WOCA also makes progress in these very high frequent on-off scenarios, where the JIT-based approach takes a lot longer time and cannot make meaningful progress. But that's just one example scenario. It could look different if you have different harvesting conditions. But we also performed experiments which are in the paper on a stable power supply, and we also have that a very low overhead for WOCA, so probably also a lower energy consumption of the system.
Thank you.
Do you have more questions? I have one question about your worst case energy estimation. what is the assumption of your underlying hardware model for the analysis?
We have first a hardware model for the system. It should be without any timing anomalies. And well, then the results can only be as good as the timing model of the controlling processor is. So if there's a lot of pessimism in that model, then we also have a lot of pessimism in energy. And for the second part, for the device modeling, we performed fine granular measurements on all the states we encountered and that we could extract from the manual of the manufacturer.
So does this mean that in your hardware there's no pipeline, there's no cache?
There is pipelines, but there are currently no caches. Yeah.
Okay.
It's a zero wait state memory accesses.
Thank you. If there's no further question, I propose let's take a 10-minute break. It's 5 minutes more than in the schedule, but I think we also need to sort the next online presentation out beforehand. See you in 10 minutes.
Okay, great.
Yeah, so you'll be going about 12 minutes. So.
One second. Can I have the mic? Okay. 中文, I'm going to prepare you for the talk. Is that all right? Okay, great.
So you'll be going about 12 minutes. So.
Okay, so let me move you. Going to prepare you for the talk. Wait, what's this delay? So we are LTES. Oh yeah, Vishnu, maybe you can do this. Yeah, just prepare 中文 for the talk.
Yeah.
Okay,
yeah,
great.
it's just like we did like a of his audio video. I'll just do this again and add him to the channel when I get the green light from the volunteer there.
Okay.
Alright, Shogun, do you want to like start over again? Just like share your screen, presentation, or whatever, start your video, just check everything. Yep, can you screen share? Okay, and yeah, like we mentioned earlier, yeah, okay, cool.
Is that okay?
Yeah, so like,
Vishnu,
yeah, it looks fine.
Do you want to move into the LTES voice chat, the channel?
I thought we still have time for that, no?
You can do it now. I don't.
I think let's move the
Okay.
It's more
Yeah.
complicated than I thought.
Alright,
Yeah.
you just want me to move in?
Yeah,
Okay.
yeah.
Alright, so Zhongwen, just like keep doing whatever you're doing, like just do the same thing in the channel, you should be good. I'm going to move you to the LC channel. Alright.
Yeah, just do it, bro.
Okay, yeah. Yep. Alright. He should.
Okay. 中文, can you hear me?
Yeah.
Okay, great. Yeah, start the camera and the slides. Okay, try again. Okay, 中文, try turning on your camera. Just your camera. Okay, this is hopeless.
Third channel.
Oh yeah, okay, just go on with the presentation. Are you sharing your entire screen, 中文?
This?
Yes. Yeah. What? Yes, this one. No, not that one. The other one.
Yeah.
The other one?
Oh, like the full screen. So are you sharing your entire screen like we talked earlier? Just like make sure that's happening, and then once you go into yeah, that one right there. Okay.
This? Okay.
The other one. Oh, you can swap your screen if you want. Okay, great, thanks.
Okay.
Yes. So welcome back to the second part of the second session of LCTES. So I think you all realize the complications, so we swap the first talk and the second talk. The next talk is going to be given by Zhongwen Fang from Chang'an University in China. So he's going to give this online due to the visa issue. So the stage is yours. You have 12 minutes for the talk, and we will have 3 minutes for Q&A, please.
Oh, can I start my presentation?
Yes.
Okay. Hello, everyone. My name is Zhongwen Feng. Today, I will present our work, TW fuzzing embedded systems with 3 valves. Firstly, fuzzing is a widely used method for discovering software defects. Google and Microsoft both use method to enhance the reliability and the security of their software. To conduct effective fuzzing, coverage-based guidance is typically used during testing. The usually process involves initializing input generation, executing the program, and monitoring code coverage. If the input covers new code paths, the input is saved for further mutation and testing. During the testing process, if a program crash exception, the input and coverage information recorded and the defect report is generated. Embedded devices touch every aspect of our lives. Therefore, it's important to test devices in advance to identify potential vulnerabilities. However, there are some challenges in
The microphone is here.
Hello. Okay. So, hello everyone. My name is Rui Taofeng, and from Singapore Management University. And today I present our work on the malicious behavior detection for IoT malware with multi-level classification. And this work was collaborated with researchers from SMU Tianjin University and Nanyang Technological University. So in this presentation, I will first introduce some background knowledge and illustrate the motivation approach evaluation in order, and then conclude the presentation. So recently, the rapid growth of IoT devices has brought convenience, but also enlarged the impact of the inadequate security mechanisms for such security scenarios. So developing certain security technologies for those IoT devices could become urgently needed to fight against potential adversaries, especially the malicious software providers. And by reviewing the state-of-the-art approaches and tools for the IoT-specific malware detection and analysis, the existing can be summarized into 2 main categories: the static analysis based binary and family classification, and the sandbox based on the dynamic analysis. But the problem is both of them have to have their own specific problems. For example, the static analysis-based classification may overlook some malicious activities in the decision-making process and always needs extensive domain expertise and efforts in the post-detection analysis. And the dynamic-based analysis offers more detailed insight which could guide further analysis, but the problem is this kind of approach always needs lots more computational resources, which the IoT devices will never offer. So based on such observation, a research question came to our mind. Can we identify the malicious behavior promptly? And we firstly conducted a large-scale empirical study on a data set of more than 5,000 IoT malware collected according to the 3 main data selection criteria from different sources. And the first selection criterion is based on the macro ratio of all data, which we want to ensure the distribution of our study samples is highly similar to the reality. And the second is to prioritize the new malware families. And the third is to select those representative samples from those highly similar clusters. In the study, this first step was the in-depth analysis of the report collected from the antivirus engine, from the virus total, and the sandboxes widely adopted by the industries, such as MITRE, to obtain the potential malicious behaviors. And further, by analyzing the report, we can produce a rough malware attack chains with the help of the TTP from MITRE attack template. And leveraging reverse engineering to Ghidra, we further statically analyze the program level implementation of each malware and summarized a detailed taxonomy of malicious behaviors consist of the stage and the behavior excavation, attack method, and the implementation of that attack chain. And this malicious behavior summarized from the real-world samples serve as the ground truth in our study and also the experiment, and plays a vital role in constructing the test dataset. And with such knowledge, we observe some interesting phenomenon. So we observed the node in the function call graph which generated from the IoT-specific malware are always farther away from the entry node of the malware. But the problem is these type of nodes contributed less and limited value in understanding the semantics of those malicious behavior, and also contribute fail in producing the malware attack chain. So we doubt whether they could bring negative impact to the graph learning method in capturing the semantics. So subsequently, we introduced a graph masking method to eliminate this type of node from the function call graph. And this graph masking method mainly consists of three steps. The first step is the central node obtaining by computing the graph centrality, and the mask radius calculation by computing the path distance between the central node and others. And finally, we can then determine the mask about which node we should remove from the FCG, which node we should keep in the FCG. And based on the graph masking method, we further proposed the overall approach, MAGRA-MAL, leveraging multi-label classification to identify the malicious behavior from malware, the IoT malware. And this approach has 4 steps. The first is the original function call graph representation, and second is mask graph construction. The third is the feature vector extraction, and finally the model construction. And along with the graph masking method, we would like to highlight another subside novelty, which is the adoption of graph structure feature. And the evaluation of this work was organized into 3 perspectives: the effectiveness of the two, the soundness of the crucial designs, and the real-time performance. The effective evaluation was conducted on 224 multi-label classification algorithm combinations, and the results demonstrate our work exhibited good accuracy but not perfect. For example, about 80% on the correctness of labels and 30% on the correctness of samples. The correctness of labels here, namely label accuracy average, represents the ratio of the correctly predicted labels among all, and the correctness of samples, namely the sample accuracy, represents the ratio of samples whose label were entirely predicted or entirely correctly predicted. And to answer the research question, the second research question, we evaluated the result of different balance parameter alpha. And in the figures on the left hand, we can find 0.7 is the matching number for our data set. And that means by applying the graph masking method, the effectiveness of this model has been enhanced a bit. And secondly, we conduct an ablation study to demonstrate the superiority of the innovation method, which is the graph masking and the adoption of the structural features. And in this experiment, we leveraged 5 different types of metrics. And for most multi-label classification method, our proposed design, our designed method has achieved a better result comparing to the result without them. And regarding the performance, we compared the runtime performance of the Lisa sandbox, which is a popular tool in the industry, and the results show that our MelGraph costs much fewer resources. However, also are able to point out the target lurking behaviors. And to conclude the presentation, firstly, we proposed a multi-label classification approach for detecting the lurking behaviors. And besides, we also released the annotated data set to the public, which cost a lot of effort. And certainly there are, this approach also have some limits. For example, we find there is a trade-off between keeping the key information and removing the redundancies in the within the mask. So we thought about whether we can have a more adaptive masking method in the future. And besides the trade-off, we also find the current approach could be easily bypassed by adversarial samples. So we believe an adaptive approach could help us solve this problem. And the third is the limited training data, because in our study we placed on a smaller size data than the reality, so it would be a great idea if we could find any lightweighted but more powerful program analysis and semantic validation method to enhance this point. So any questions?
Okay. The next speaker. Any questions? So I have a question about the data sets you use. Do you have all the malicious behavior precisely described, or they still have some undescribable behavior, but still malicious?
The methodology used to build the ground truth is we start from the malware report, and we use as the guideline. But after obtaining and analyzing the report, we dig into the implementation of the malware by reverse engineering the malware and analyzing the code. So basically, in short, our ground truth was built upon the malware, the sample analysis.
So this means that you still have false negative, right? Because not everything is correctly reported for the negative side. There could be some unfound malware functions.
Yeah.
Okay.
Because it is quite a huge effort in analyzing those malware. So with our effort, we can only handle like as much as 5,000.
But you mentioned that you did that manually, so you did it 500 5,000 analysis manually or with some automation?
Basically, it was conducted manually, but we use the report as a guidance. That is why we start from the like using the static analysis to build the FCG and also use the regenerated report as a reference, as a coarse grain malicious behavior explanation.
But this means that this method is not possible to be extended with larger data, right? So if you have to do this manually.
Yeah, we are thinking about this, we are thinking about any potential extension from this point, because if we can solve this problem, we can automate the whole process and save a lot of human effort and maybe try some novel machine learning or deep learning method on a huge data set.
Okay, any further questions or suggestions? If not, then next speaker again. So, please. I'm searching for the last speaker today. Okay, sorry. I think we use the whole break time to set up the online presentation. I'm sorry I did not actually conduct the biography of the speakers of the second part of this session. Yes. So the next talk is going to be OpenMP with real-time support. It's on already.
Okay. Is that working?
Yeah. Okay. So it's going to be given by Bryden McDonough from North Carolina State University. So the stage is yours. I suggest you to take this with you, otherwise this will fall apart.
Okay, there we go. So, yes, I'm presenting OpenMPRT, native pragma support for real-time tasks and synchronization with LLVM under Linux. So the reasoning is that this is for real-time systems that are under strict timing constraints and during development, more specifically, predictability of timing, or constraints on the predictability of timing. With them being increasingly prevalent and an increasing desire to leverage multi-core systems for use in real-time systems, there's a use case for real-time multi-core programming framework. So since they're subject to timing constraints at runtime and predictability of execution time, parallel systems obviously leverage multi-core architectures for performance improvements. There's difficulties in combining the two due to many existing frameworks for parallel issuing certain real-time guarantees. One example just off is in unmodified OpenMP, the priority or assigning a priority to a task in OpenMP is actually just a suggestion according to the specification, which works fine for OpenMP but not for real-time systems. So I can skip this slide. This is from something else. So the objective here was to develop a framework for creating parallel real-time tasks, to reduce the code complexity in creating real-time tasks. There's a comparison slide for that. And to support both coarse-grained and fine-grained parallelism. In this case, that means coarse-grained, i.e. tasks themselves executing in parallel on separate threads, as well as fine-grained being individual tasks being composed of multiple threads operating in parallel. And then implement synchronization methods for inter-task communication, sharing across these parallel tasks. So for this, we have the RT task concept, a pragma that we've inserted into modified OpenMP runtime to enclose a single periodic real-time task. We leverage the kernel scheduler for actually scheduling this task So in our current implementation, it's restricted to Linux because Linux, with the preempt RT patch, does already support EDF, earliest deadline first, and static priority scheduling for threads. And then we incorporate lock-free synchronization via two separate methods. Specifically, though, we have a per-priority thread pool and lock-free synchronization to allow for multiple scheduling paradigms to coexist separately. In this case, we can have both EDF tasks scheduled under EDF, earliest deadline first, and static priority tasks existing separately, as well as, of course, lower priority real-time processes. We do cover that in the synchronization, but actually scheduling them is outside the scope because that's a studied problem. So the RT task construct with an example implementation, or an example invocation of it there, is associated with a single dedicated periodic real-time thread. It may pull from its given priority or from the given thread pool for the EDF priority band if it expresses fine-grained parallelism. But it is the pragma encloses the code for a single RT task. Notably, it's associated with just a name rather than any of the information required for the expression of a real-time task. That's abstracted to a configuration file that I'll go into in a little bit. This, as you can note, incorporates fine-grained parallelism as well by enclosing an OpenMP parallel section containing two threads, and then using the OpenMP task pragma internally. To express the code reduction when invoking an RT task. So this is an example, or the code example on the left is what is the sequence of calls used to express a EDF task in Linux right now. Then using RT task, this is what that ends up looking like because everything on the left is abstracted to the modified OpenMP runtime and to the code generated by the LLVM compiler. So to express how the thread pools work, RT tasks at a given level of priority pull from a shared pool of threads. The size of this pool of threads is determined at compile time. So thread pooling does already exist in OpenMP. Let me see. Yes. So to express for contention over an example of an issue that can come up is in contention over threads pulled from the shared pool with shared processors. So in this case, assuming that both the red and blue tasks are on the same priority level, we show here that when assuming they both express fine-grained parallelism internally and share 2 of the 4 available cores, in this case, it's non-deterministic which task will enter its parallel section first. So we end up with this contention and then unpredictable runtime. Red, in this case, effectively is single-threaded, and that violates earlier what we want with periodic runtime, or with, not periodic, sorry, predictable execution time. So to combat that, you'll note in the configuration file does establish the configuration file is passed in with the program in addition to the source code. And this is used to tie the name of given RT tasks to the actual real-time properties, period, execution time, phase, and depending on, and the actual scheduling paradigm that it will be under, either EDF, in which case there is no priority passed in, or static priority, in which case there is a priority listed. As well as defining the both the cores that are available to this, to each given thread, or to each given task, sorry, each given RT task, and thus the threads that it pulls from the pool, what cores they can be assigned to, as well as defining the shared variables for task synchronization, sharing data between RT tasks. And so the reason for specifying the cores is specifically to avoid the problem we see here. Since if we go back in this slide, we can show that by partitioning the cores separately, we avoid that contention here, and thus our worst case time for red or blue, because this could have gone the other way, is significantly improved. So, so this is the project structure with both the application code and the configuration being passed into the LLVM compiler, containing the modified OpenMP runtime to produce a binary executable with OpenMP-RT. So for the intertask communication, there are two methods for OpenMP-RT, a retry-based method and a double buffer-based method. They have some advantages and disadvantages that I'll go into. There was a lock-based deadlock-free method using a total ordering of locks created, purely to compare with the two lock-free ones. That also shows up in the data. So for synchronization using the retry method, there's read and write pragmas that can be invoked from within an RT task or outside an RT task for communication across the real-time barrier. We use these, or the way these work is by updating, there are 2 timestamp registers associated with each dependency variable. We don't really specify there aren't limitations on the type or size of the dependency variable. That's just passed into the pragma. But with 2 timestamp registers, on a write attempt, move out of the way here. On a write attempt, the top timestamp is overwritten, and then data is written. Then at the end of, or once the write is complete, the timestamp value from the top will be copied to the bottom. Or rather, the red timestamp value will be written to the bottom. So both timestamps should, on a successful write, have the same value. With a read attempt, we can check the top timestamp, read it, and then check the bottom timestamp. And if the bottom timestamp is different from the top, this indicates the data was invalid. Either a write attempt went through during or either the write attempt went through during the read and thus invalidated the data that was read, so read has to go back and attempt the read again. This retry on the read will continue until either the maximum number of tries is exceeded, in which case the read fails, and it's up to the programmer inside their RT task or inside their code to figure out what they want to do from there, or until you get a success. The maximum number of retries is configurable. So for the double buffer synchronization, this has greater space complexity, requiring 2 buffers instead of just 1 to write to. And then a single pointer field. This is per dependency. This, incidentally, is why dependencies do have to be listed in the configuration file so that this can be set up at compile time. So 2 buffers with a single pointer field. At any given time, one of the 2 buffers is considered readable, the other writable. So on a write, the writable buffer is written to, and then the pointer value is swapped. Then a read just simply checks the pointer value, reads, and then we'll simply check the pointer value and read. This prevents the reads from failing, but does have increased space complexity in memory. So for the experimental analysis, we targeted specifically the C language. C++ support should be in there, but our test code was all in C, so for now we say C language support. With experiments conducted using synthetic applications generated using or containing multiple RT tasks expressing both, or always expressing coarse-grained parallelism, but also in some cases expressing fine-grained as well. These synthetic applications were assembled using using applications taken from the BOTS, Barcelona OpenMP task set, and the EPCC benchmarks as component RT tasks. So each of the small ones taken from those benchmarks would be used as a single RT task, and then a synthetic application would be composed of just multiple RT tasks smushed together. The table here just shows the worst case execution times for both sequential or two-core fine-grained parallelism versions of each of the benchmark tasks. So each one of these would have been one RT task. You can look at the actual benchmarks to see what each of these do, but some of them, like the FFT, is fairly obviously the fast Fourier transform. N queens computes the number of queens on a chessboard. And so 100 randomly generated test applications were used. For utilization stress tests, see how high we could crank the utilization of a OpenMP task set before, or OpenMP RT task set before we had failures and deadline misses. We got up to 0.93 or utilization per core. So utilization in this case was uniform across cores for our 4-core system. So this is a per core utilization of 0.93. And we were able to get that high without any deadline misses at anything below 95% utilization on per core. So for comparing the intertask synchronization methods, in this case, an application with 4 RT tasks on 2 cores in producer-consumer pairs. And in this case, transferring 64 by 64, or 64 byte by 64 byte matrices between pairs. So there are 3 cases. This is looking at both across or within real-time applications and then across the real-time barrier in both directions. So, and then recording the average response time for consumer tasks, since producer tasks are less limited on that one. We did record the producer tasks, but they were similar in, or the data was of the same shape. It was basically the same, so it was cut from this presentation for space reasons. And so that could actually be bigger on the slide. Significantly lower response times were observed using the lock-free methods than the lock-based methods. Specifically, the double buffer had the best response times. And this, I'll note, this is utilization. That's total utilization, not per core utilization, which is why it starts at 1.2. And so the improvements aren't really visible until utilization gets fairly high, which for obvious reasons. When utilization is fairly low, not a lot of the response time is limited by contention on intertask synchronization. For looking specifically now at the retry-based method, because it has the non-deterministic reads that may or may not fail. So in this case, we have a 2 RT task system on 2 separate cores, just communicating across cores, recording the number of failed read attempts versus the ratio of the producer period versus the consumer period. In this case, just representing, say, a sensor with a high refresh rate, sending data to some internal process in a machine. And in all three cases, for the whether or not this data crosses the real-time barrier, it's fairly similar in behavior. So the frequency of rereads does increase as we expect with the, okay. This is basically my last slide anyway, so that works.
Okay, thanks. Okay, questions? We have no time limit, right? Because I have a lot.
Oh, I see. What did you do for the lock-free programming? How did you implement it, and why the performance is like this?
So with preventing deadlocks in the lock-based one that we compared to, or just an explanation of the lock-free communication method? Yeah. So the lock-based one that was deadlock-free was just using a total ordering of locks based on the order in which dependencies were accessed within the program. That was just for comparison. That used the lock API that's just provided in Linux. For the lock-free ones, with the two of them, those were implemented using atomic instructions where necessary, such as for updating the timestamps. In fact, such as for updating the timestamps or updating the pointer value here, and then.
How do you know they are atomic? I mean, on what machine are you running this? How do you know they are atomic?
The atomic instructions, just using the, what is it? I'll have to go back and look I'll have to go back and look in my code, but using the atomic instructions, this was running on an x86 machine. So I'm not actually certain how the atomic instructions at the level that I'm writing this are implemented on the hardware, but I do know that atomic compare and swap is provided to C programming on Linux running on x86 machines.
Further questions? If not, then I have one. Actually, many. So I ask one of them. You mentioned that you use Linux, right? But OpenMP can also be executed on RTEMS as a real-time operating systems as well.
Yes.
So which specific operating system support you need in your approach from Linux?
The reason for that was that our modification to the OpenMP runtime leveraged specific calls used by the Linux scheduler. This could be done on other operating systems that provide real-time scheduling at the operating system scheduler, but A, that's an implementation problem. That's something that we need to extend our implementation for, and B, it does need to be provided in the operating system.
But can you roll back to
Yes.
what you said earlier about the scheduler of Linux? It's actually this one only, right?
Yeah.
So of course, every operating system has its own scheduler and specifications of task control block, but you can actually adapt to that, right? So maybe you can have a look of other operating systems that currently already support OpenMP. So it could be a general approach that you have proposed, but
yeah.
Okay. Any more questions? If not, then next time speaker. So I think we are asking Yuli to be the next session. So the speakers.
So this is the final one for this session, right? So we come back.
So I forgot to close the session again. Sorry for the. I apologize for a bit chaotic order of organizing this session due to the dynamic structure of the whole session. So the session is closed, and I'm just handing over to the next session chair, who is also not here yet. So I guess the speakers of the next session should come to talk to him first.
So, who are the speakers? Feel free to come to me, please.
Yeah, just for testing. Okay. Let me just check something. Okay. Yeah. Okay.
given by Wei-Min Chen. So Wei-Min comes from Polytechnical University of Hong Kong. He's currently a third-year PhD student. His research interests including smart contract security as well as CUDA programming. So let's welcome Wei-Min.
So thank you. Thank you for the warm introduction, and Wei-Min, good afternoon. Today I'm going to present our work about the binary translation scheme from upgrading EVM smart contract to Wasan, or we say WebAssembly. It's a blockchain paper, so let me introduce the blockchain first. The blockchain is a decentralized database, you can see, and each data block it can contain kinds of data like the address and the balance of the account, and different data block can be connected by the hash value, so that it can contain the entire database can contain some blockchain features. And the most popular one blockchain is the Ethereum. It is most popular one, and the total market value reached over $15 million. And this because it is the first blockchain that can support the smart contracts, which is a kind of computer program running on the blockchain. It made the blockchain programmable. So basically, the Ethereum smart contract are written in the source code in Solidity, as so in your left hand, and it can be compiled into the bytecode, so in your right hand. And this kind of bytecode is actually the program that running on the blockchain, and will be interpreted by the virtual machine called EVM. But EVM have some disadvantage by design. For example, there's no function support, and it may suffer from the DOS attack because all operation on the EVM is 215 bits, so everything running on the EVM is expensive. And some companies want to use a better runtime to replace EVM. That's what we call WebAssembly. Actually, WebAssembly is first designed for the web rather than the blockchain, but this company believes WebAssembly with better language for the web smart contracts. Yes, safer environment for executing the program, and more language support the Wasan generation. And it also means the WebAssembly program has a better performance. Here are some blockchain that have moved to WebAssembly runtime. And when the new blockchain appears, the first important things for them is to attract enough developers to write the smart contracts for this new blockchain. And so they have some idea to migrate the smart contracts from the Ethereum to their new blockchain and foster the prosperity of Ethereum. And here there are some efforts. You can see if there is a Wasan runtime there, and given an EVM bytecode, how to run them on the Wasan runtime without EVM. So for the NIA and the Polkadot, these two kinds of blockchain, they want to compile the EVM to a Wasan smart contracts, and then use this EVM smart contract to interpret other EVM bytecode on the Wasan runtime. So there is a bridge between the EVM bytecode and the really execution virtual machine. So there must be some overhead there. And another competitors like the SOL and so on, they want to design a better compiler which can directly compile the Solidity source code to the WebAssembly bytecode. However, we found that there are some compiler issues in these two baselines. They cannot handle all the grammar features that introduced from the Solidity compiler, I think. And what we want to do is the EVM-BT, which is a binary translation, which can directly compile the EVM bytecode to the Wasan bytecode without any without any EVM support. So this is architecture of our papers. Basically, we want to extract the runtime code and the constructor from the bytecode, EVM bytecode, and then leave them to the LVM IR as the intermediate representation. then we'll in the LVNIR to support various of ECRN support so that the generated smart contracts can use the ECRN runtime and then run on the WebAssembly at the same time. And at last, we will use LVM backend like the C-Lang to generate the WebAssembly blockchain. So there is the overflow pipeline. The bytecode come in here and we lift to the LVM assembly. At last, we generate the WebAssembly bytecode based on the translation rules defined in this table. And I give an end-to-end case here, and if you are interested, you can see our paper for more details. So let me introduce our technical in this simple example. So in this smart contract, there are only two opicals, push and issue. Namely, the first opical will push an immediate and a data into the stack, and then issue will determine the value of data whether is zero. If it is, it will push the zero. It will push the one into the current stack top. To lift the stack-based language to the LVNIR, we had to use the devirtualization technology to make them to generate a register-based LVNIR register IR. And here is what we do. We will use LVN ArrayNet mule as the emulated event stack, and use another register net P to check the current stack depth. So the mule P is always point to the memory of the current stack top. So for the push data, this EVN opical, we can translate into these two lines of LVNIR, which first will add the register of P by 1, and then store the data from the push data to the current emulated EVN stack, which is the mule P. And for the issue, you need to check the data on the current stack top, so we need to pop one data from the mule, which is the third line, what we do. And then we use the LVN instruction to do some to compare the data of the C and store the result back to the stack, which is the mule P. And obviously, we can infer the operands at the compile time so that we don't have to access too much the memory. It's a little bit like memory to register. So in here we can see the operand used by the issue must be the data pushed by the previous opical. So we can directly compare the result of the data directly and then push the result to the stack. In this case, it has equal functionality, but it has less memory access, so it's more efficient. This is what we do for the entire papers to reduce the redundant LVNIR instructions. And for the control flow, we also do some optimization for that. All event jumps in the bytecode are actually indirect jump, so it's quite challenging to recover them and translate them into LVNIR. To do that, we lift all the event jump to the table jumps and just like using the switch instructions, and then we will approximate all the possible destination of the indirect jump so that we can ensure the translation code must be correct. And of course, if there are some situation, then we can solve the indirect jump to the direct jump. We will do that using the symbolic execution. Here's just a simple case. In here, in your left, there is the bytecode, and then we can apply symbolic execution to it and calculate the destination of the jump in the 05. You can see the destination of jump must be EF because it is added by the EE plus E1. So when we finish all the optical EVN instruction translation, we implement our tool EVM-BT and write experiments for it to evaluate the performance. We have a special testbed which equipped with the EVM and the Wasan runtime together, so we can replay the transaction, EVM transaction on the EVM and the Wasan together, and then compare collect the trees and then compare their difference to see whether the EVM-BT has the correct implementation. And we also collect two kinds of benchmark. One for the large benchmark, which consists of 2,000 smart contracts and their transactions. Another benchmark is the synthesis benchmark. In the large benchmark, we found that when we replay the smart contract of EVM and the Wasan on our testbed, we can find out the similarity score of the EVM trees and the Wasan trees is almost 100%, and there are still issues I think maybe caused by the implementation issues. But anyway, the result shows that EVM-BT can retrieve high semantic correctness in translation. And we also want to mention the overhead of the EVM-BT, as is the binary translation work. And in terms of guess overhead, or guess is the matrix that measuring the matrix measuring the execution cost in the EVM. And so in terms of guess overhead, we found that EVM-BT introduced a low overhead, which is less than 1%, and it demonstrates the similar guess efficiency as the source code compiler baselines. But the time overhead a little bit strange because we find that it is the smart contract generated by our tools is 136 times slower. We want to know why. We guess. So we think the main overhead is caused by the Wasan runtime rather than the binary translation. To prove that, we collect a synthesis benchmark which conclude 14 computation tens cases, and then we run them on the EVM and the Wasan runtime to compare the time. We can find that EVM-BT can achieve a speed range for the 1.05 to 1.2 times faster, and while the baseline introduced much more overhead. So that's my conclusion. So we design EVM-BT, a novel EVM to WebAssembly binary translation framework, and we conduct extensive experiments to evaluate EVM-BT by replaying the transactions on both EVM and the Wasan runtime. This shows that the accuracy of our tools, and it also can generate a similar guess efficient smart contracts as the source code compiler. So here the reference. That's all. Thank you, everyone.
Any questions? I have one quick question. So your technique works on one smart contract, but does it generalize?
Yeah, general point.
To other smart contracts?
Yes.
Okay. All right. Thank you.
Thank you.
Second talk will be given by Li Chenjia. He's from Institute of Computing Technology, Chinese Academy of Science. His presentation will be on code extract, enhancing binary code similarity detection with code extraction techniques. Let's welcome our second speaker.
Sorry, wait a minute. Need to clean the. Good afternoon, everyone. My name is Li Chenjia. My paper title is Code Extract Enhancing Binary Code Similarity Detection with Code Extraction Techniques. Learning-based binary code similarity detection method, short for LBBZD, method has become the mainstream method for similarity comparison. Its detection speed and accuracy has surpassed the traditional binary code similarity detection techniques. This technology serves as a pivotal support for numerous security applications, and its accuracy directly impacts the security of these applications, including malware detection, software plagiarism detection, vulnerability management, and pattern analysis. The learning-based, the LBB technology follow the structured workflow. The LBB technology follows a structured workflow that begins with the disassembly of executable files. This process transforms the binary code into assembly instructions, often focusing on individual functions within the code. Once the assembly instructions are obtained, they are then analyzed to construct a equivalent control flow graph, sort of a CFG. The CFG captures the flow of the execution through the functions, represented by nodes and edges that signify instruction and their transition. Okay, thanks.
And keep this in your pocket.
Oh, okay, thanks. Hello? Oh, okay, it's good. The core of the RVB method lies in the encoding of the nodes and edges within the CFG. This encode process transforms the graph structure into a point in a vector space. The point serves as a representation of the function's semantics, and its position in the vector space reflects its characteristics and behavior. By comparing the distance between points in the vector space, RVB can determine the semantics similarity between functions. Function with similar points in the vector space exhibits similar behaviors and functionalities. For instance, if a non-malicious software function represented by ordinary point in the finger it is detected, RVB method can identify other functions that are semantically similar, indicating potential malicious intent or functionalities. Function learning has been identified as a significant challenges for RVB technologies. To investigate this issue, we selected three state-of-the-art RVB models: ASM vector, safe, and G-trans. We evaluated these models under two scenarios: one with function inline inboard, this is represented by WI, and the other with functions inlining disabled, sort of NI. When function inlining was disabled, the average accuracy was modeled at 80%. However, upon enabling function inlining, the average accuracy dropped to 50%, indicating a 30% decrease in accuracy. So why does function inlining affect the accuracy of the RVB method? There are two reasons. Reason one, function inlining inlines the callee function code to the function call point. This will increase the complexity of control flow graphs and increase the number of instructions. Reason two, different optimization options of the compiler involve different levels of function inlining, which lead to significant differences between different versions of the same function, O1 and O3. The detect results. Functions are often called multi-terms, and because function inlining introduces callee code at multiple call points, it can lead to duplicate code in the program. Therefore, we can use the method of extracting repeated code to extract inline code into function calls. So in that finger, the function destroy quantum pixels is called by two functions: set quantum depth and destroy quantum info. After function inlining occurs, the CFG structure and the instructions of the inline code are highly similar. Our solution feasibility analysis So wave function inlining introduces duplicate code. When the function is called only once after inlining, no duplicate code is introduced. In the finger, function C is only called by function A. In this case, when function inlining occurs, no duplicate code will be introduced. In this situation, this study proposed an proactive inlining techniques that inlines all functions that are only called once. So when a function is called more than once, function inlining does not necessarily introduce duplicate code. In the left finger, function C is called by function and function B. After function C is inlined, there exists duplicate code. Duplicate code is basic block C2 and C3. But in the right finger, function C is also called by function A and function B. But function C is relatively complex. It has left pass and right pass. Left pass is C2 and C3, and right pass is C4 and C5. After function C is inlined, the left pass is inlined into function A, and the right pass is inlined into function B. So function C is inlined, but there is no duplicate code. This is because different parts of the function C are inlined. So after inlining programmed in spec 2017, it was found that for functions that are inlined multiple times, over 92% of them are inlined with the same basic blocks, while only 8% are inlined with different basic blocks. So our code extraction can solve more than 92% of the inline basic blocks introduced by multiple inlinings. So our solution has two parts. The first part is proactive inlining. This scheme will inline functions that are only called once. The second part is code extraction. This scheme solves the problem of functions that are called more than once. So the system framework diagram of code extraction is binary programs are first disassembled to their corresponding functions. The functions are then processed by the code extract modules, which remove the inline code to produce normalized functions. These normalized functions serve as the input for the LB-based models, which facilitates function matching. Within the code extraction scheme, the filter module initially identifies the basic blocks introduced by function inlining. And the similarity calculate modules analyze the similarity between the inline basic blocks and identify the similar ones. Finally, the repeated code extraction module extracts the repeated basic blocks within functions, resulting in a normalized function that includes redundant code. But we have two challenges. Challenge one, identifying duplicate code relies on calculating similarity at the basic block levels, which incurs significant overhead for pairwise similarity calculation. Challenge two, the compiler optimizes inline code, such as register mapping, which can lead to a significant difference in similarity between the same basic blocks in different contexts. Solution to challenge one, inline code will have a unified entry basic block, such as in a finger, the entry basic block. The basic block introduced by inline can only be the entry basic block and its descendants. So the blue box sections represent the inline basic blocks. If we restrict the similarity calculation to only comparing the 6 basic blocks on the left and to the 6 basic blocks on the right finger, rather than computing similarity with all basic blocks in left and to the right, we can achieve a substantial reduction in computational overhead. So the solution to challenge two, the compiler will optimize the inline code, which leads to after the same basic block is inlined, to different call points, the register name has changed. For example, in call site 1. The REX register is assigned the memory value pointed to by the RCX and served as the first operator of the sub instructions. At call site 2, the register used turned to RCX, but RCX is also assigned to the memory value pointed to by RCX and served as the first operand of the sub instructions. Therefore, we will analyze the define use behavior of the registers and rename registers with the same define use behavior. Another challenge is after a same basic block is inlined to different call points, the registers are optimized into immediate values. For example, the RCX register is optimized to 8. So we will analyze the content values of the registers and determine whether it is equal to the immediate values. So this is the experimental evaluation parts. We will evaluate the accuracy of the LV-based models is improved by code extract. So our conclusion then is that the code extract can increase the accuracy of the model by about 20%, and the inline emulation scheme can only improve the accuracy of the model by about 10%. This part is the impact of the number of inline basic blocks on the accuracy of the LV-BCD models. When the number of inline basic blocks is less than 3, the impact on the accuracy of the model is only 3%. When extracting duplicate code, we will extract code fragments with a basic block counting 3 or more. This is the analysis of false positive rate and false negative rate of the code extract. Our conclusion is that for all functions, the false positive rate and false negative rate of code extract are higher than those of inline emulation. However, for functions with a basic block count of 3 or more, the false positive rate and false negative rate of code extract are lower than those of inline emulation. Thanks for your listening. Any questions?
Questions? Yeah, go first.
Oh, okay. Really interesting stuff. Are you doing this analysis at the machine code level? So are you looking at the machine code instructions or some sort of intermediate representation?
I do it at this assembly code. I think machine code is short code. Short code is compiled to a binary, and then binary is this assembly to assembly code. So I do it at assembly code.
Okay, so my question was going to be then, like, how do you recover basic block information? And are you doing that by looking at the assembly language text?
Yeah, yes, yes.
I understand. Thank you.
Oh, thank you.
One more question.
Have you tried to do another round to say, for this unoptimized code, you optimize it. So you inline this code and compare with those already inline code and compare that to the
Yes, this is a very interesting question. In fact, I find slides. This is real cases. Why we extract similar code is because inlining will introduce the same code at different call points, so we can extract duplicate code, so we can solve the problem of inlining. So you suggest me to inline some functions. So this will be easier to solve this problem. So this is a big challenge is which function should be inline. If we inline all functions, then we only one function left. This is the main function. So we don't know, we will have to do the same choice with the compiler, but the compiler inline strategy is very complex, and we cannot simulate every choice of the compiler, so it's hard to make it the same. Thank you.
Okay, any other questions? Okay, so let's take. So our third talk will be given by Professor João Bispo. Dr. Bispo is currently an assistant professor at the University of Porto. He received his PhD from Lisbon Technical University. His research interests focus on source-to-source compilation. Let's welcome third speaker.
Yeah, thank you very much. So, thank you. Here. Okay, can you hear me? Yes. Yeah. Let me just prepare. Okay, so good afternoon. I'm here to present foundations for a Rust-like borrowed checker for C. So first of all, this is the work of a master thesis by Tiago Silva. He was the master student, but he could not be here today, so I'm going to present his work. I'll give an overview of the work. The technical details will be in the paper, okay? So first, why do we care about memory safety? It will not be a surprise to anyone if I say that C is an unsafe language, a very unsafe language. And if we go to the CVEs, we can see the vast majority of them every year is about memory issues, okay? So there are several problems to solve this. One of them is, for instance, having a language that does not have the same problems that C has. That's what languages like Rust and Go do. However, even if Rust is gaining traction, C is not going anywhere so soon, so we have to deal with it somehow. So the idea of this work is, can we replicate Rust's memory safety guarantees, but over C code? Okay, so first introduce some concepts. Rust uses a borrowed checker, which is a tool that enforces statically at compile time if certain properties are present in the code. Rust itself has been having several iterations of this borrowed checker. So every one of these iterations are sound, so they all they do not allow wrong code. But the difference between iterations is that each one tries to have false positives, okay? So the difference between the first one and the second one will be, the second one will try to, you have Rust code that it's okay, but the borrowed checker might not be able to understand that it's okay. So this is what each iteration has been doing. The work that I'm presenting is based on the non-lexical lifetimes version of the borrowed checker. There's also a newer one being developed, Polonius, but this is still very recent. So we went for the more mature one that's currently being used, which is NLL. Okay, so some basics about Rust so that we understand what kind of analysis we will be doing. There will be a quiz later, so pay attention. The first thing to understand about Rust is that every read is a move, okay? So that means in that assignment, A equals B, we are moving the value of A into B. Or if you give A to a function call, we are also giving we are moving the value of A inside the function call. There's an asterisk here. If it's a type that implements copy trait, it's not a move, it's instead a copy. But for copies, there's no problem. The problem is when we have pointers, references. Okay, so that's putting that aside. Let's consider only moves. And one key idea is that after a move, the original value is no longer valid. So when I do B equals A is no longer valid. Okay? But sometimes I don't want to move. I just want to borrow the value. That's where this concept of borrow comes from. In Rust, you have syntax for this. The ampersand is a simple borrow. And you have also a mutable borrow if you want to let the variable change or mutate the value. We can condense what's happening on this table. So, for instance, if we borrow the value to another variable, every variable can read, okay, and you can have several of them, and you can reborrow. Your borrowed value can be reborrowed to another variable, but you cannot change it, okay? Until all the borrows have finished used, there's no changes that can be made to the code, okay? When you do a mutable borrow, you are giving permission to write, and only the owner of that mutable borrow can change the code and read it, okay? So that's how we can ensure some memory safety concerns. So all those rules have the following consequences. So values must be initialized before they are used. No uninitialized values are not allowed. You cannot move a value twice, because if you move it once, it becomes invalid, so you cannot move it again. If a value is borrowed, you cannot move it, okay? Only after all the uses of the borrow. If it's mutably borrowed, you cannot access. And if it's borrowed, you cannot mutate it. So this derives from the previous rules that I've shown. Okay, so quiz time. This Rust code has an error. So I'll give you 15 seconds. If someone discovers the problem, please tell me. Okay. Wrong, sorry. Foo equals 4, it's okay, because you borrow foo into P, right? And then you use it. But P is no longer used in that branch, right? Because bar overwrites P. So P is no longer being, you are not, so the problem is not the 11. Any other suggestion? Okay, that one in yellow, who was first? Exactly. So that's the answer. The thing is, the first borrow inside the if, P after the last use of P is on line 10. Because it's rewritten in 13, P disappears after 10. The borrow ends there. But after the if, P is still being used on line 17. So you cannot mutate while it will be used. So this is the kind of analysis that the borrow checker of Rust does, okay? And it outputs error messages like this. And our objective will be having messages like this, but for C code, okay? How does Rust does it? So Rust has a couple of internal representations. One of them is MIR, which is basically a CFG. And it's over this CFG that this analysis is done. So now I'll introduce Coral, which is the tool you developed for this work, where we replicate this behavior, but for C. So in Rust, you have special syntax for specifying what is a borrow and a mutable borrow. We don't want to change C. We want to use C exactly as it is. And so instead of having special syntax for the borrows, we are using the types of the variables to distinguish between what is a borrow and what is a mutable borrow. Okay, so for instance, we have this code. That was the previous example. On the right, you have C code equivalent to that Rust code, and we want to detect the same kind of problem. How are we doing that? So we are using a source compiler, this Clava, which was developed in our lab. And one special thing about this compiler is that we can extend it without modifying it. We can write compiler passes in TypeScript that are interpreted by this compiler. And Coral is basically a TypeScript, JavaScript library that was implemented that will be executed by this compiler. So there are two phases in this compiler, in this library. The first one is normalization or canonicalization of C code. So in order for the analysis to be simpler, to simplify the analysis, we first do some automatic transformations on the C code, okay? For that, we are using previous work. It is another library for Clava that does that kind of normalization. Then we build the CFG, similar to what happens in MIR, and it performs the same analysis with the same restrictions and inference of lifetimes. Okay, so after all that, this is what we are obtaining. So if we give that code to Coral, it will output a very similar message as the one that Rust obtains. It uses the same three-point narrative. It's how they call this format, this message format. And most of this work, but again, this was done during a master thesis. And just to explain, in Portugal, a master student has around 4 or 5 months to dedicate to the masters. And most of the work was understanding how the Rust borrow checker works. It was not easy because although there are a lot of information, it's scattered in many RFCs, in many documents. We also had to check the Rust source code to understand sometimes what was going on. So one of the main contributions of this work is gathering all that information, and that's why this is called foundations for a borrow checker. But even with that, we could implement some of these checks. And I can say that we have already, after this, we continued the work, and we have submitted an extension to the text journal where we have already been able to implement most of these points, and we will continue to work on this. Okay.
Thank you so much for a great talk. So I have actually 2 questions. One is that why didn't you do in the LLVM level? Why did you do that in the C source code level?
Okay, so for several reasons. One of them is to avoid being tied to a specific compiler. So because we do this at the source level, then we can just do the check and give the source code to GCC, CLang. So that was one of the reasons.
And my second question is that I believe that the power of the Rust type system license is support for unsafe features like interior mutability. So do you have a plan to support interior mutability that is understood in some semantic types in Rust?
Sorry, what was the term that you said?
So interior mutability or unsafe features Rust is, I think, one of the most important features in its type system. So do you have a plan to support that?
Okay, so first, this first work, we were trying to follow Rust rules very closely, but in next work that we did, we tried to make it more native to C. Okay, so the objective is trying to be as close as C as possible. For instance, in Rust you don't have nulls, but in C you have nulls. If you forbid nodes in C, you will not accept any code. So we are thinking about techniques to handle that. But of course, one of the things that we want to support is boxes, okay, to handle the dynamically located memory, and of course arrays and slices.
Okay, thanks for a nice talk. I've a question regarding how you actually translate C programs into the typeset programs like you presented. Can you do this automatically or it has to be done manually?
Okay, so for this work, we were requiring some manual changes, but right now we are, for instance, we are no longer asking people to put the restrict. We'll try to infer if it's needed or not, if it's a mutable borrow or not. Also, there's a pragma-based language to annotate lifetimes, but we can also infer most of them. But if the tool cannot automatically infer, you can go there and indicate what are the lifetimes of the function. So, but the idea is trying to automate as much as possible.
And in your extension, you also mentioned the possibility to use heap, right? So how generalized is that? Because you can do whatever crazy stuff there, right?
Yeah, so that's an open question. I can check. This is our current progress.
Yes.
So that will be the next.
As I understand it, to do some of the fancier array and slice memory safety things that Rust does, it basically just like calls into unsafe and then does whatever in provinces it's safe. So would you try to infer that for C? Like what? I'm curious about the arrays and slices point, really.
If I could understand correctly, you're asking the reason for slices? No.
So like Rust, as I understand it, to make things like array.split or whatever that like gives you two chunks of memory that like guaranteed are not alias to each other, like it does some unsafe operation and then just hands you back 2 pointers and it promises that they're safe. And so I'm wondering how you would do this in C.
It's not done yet. We have some ideas of how to implement it. So the idea of slices is also so you don't... okay, so if you give an array without slices, you are basically borrowing the entire array. So the idea of slices is just to limit what you are borrowing, right? But as I said, we already have ideas for this. Let's see in future work what we can do about this. But there's plenty of stuff right there. Unfortunately, it's the students who know the technical details about this. But there are planned solutions at least. Okay.
So next talk will be presented by Rita Feng, who is currently a research scientist at Singapore Management University. He obtained his PhD at Nanyang Technology University. So let's welcome our next speaker.
Hello everyone. I'm Rita Feng, and in this presentation, I will introduce our work, namely enhancing code vulnerability detection via vulnerability preserving data augmentation. And this work was collaborated with researchers from NTU and SMU. The graph neural networks has been widely used in detecting software vulnerabilities, and the main of the ideas of such works is using the graph neural networks to learn the code semantics for the vulnerability detection. And through our broad literature review, we observed those most existing work ignore the specific types of vulnerabilities. They usually mix all different they usually mix vulnerabilities from different types, such as CWE, for example, the buffer overflow and memory leak together to train the classifier. But the problem is, the reality is that the different types of the vulnerabilities usually have different types of characteristics. So it's raised a question, can we train the classifier for each type of vulnerabilities? So by reviewing the existing CVE report, we observed the different types of vulnerabilities are extremely unbalanced. For example, there are more than 20K CVEs under the category of memory corruption, but there are only around 900 for the file inclusion. So to address this type of issue, we proposed the FG welded consisting of 3 sequential parts. The first part is the data collection, and the second is the vulnerability preserving data augmentation, and the third part is the edge-aware GGN construction. To collect the data set, we firstly gather the commit related to the vulnerabilities, and then extract the vulnerable and non-vulnerable functions from the commits. And for the vulnerability-related commit collection, we firstly define a list of keywords and use them to filter out our targeted vulnerable functions. So in all, we have collected 5 types of CWE data, vulnerability data, including CWE'24, 835.120, 672, and 362. And for each type of CWEs, there are several keywords to help us to retrieve the vulnerability-related commits through the message matching. And as I introduced, it is quite difficult to ensure that each type have a sufficient number for the learning phase. So we propose a data augmentation technology to scale up the collected data, and also keeping the semantics remaining unchanged. And this vulnerability preserving algorithm consists of 2 steps. The first step is that after slicing the original function to get the vulnerability-related statement, we conduct the forward slicing on the program dependence graph to find the future dependent statement. And afterward, we further conduct the backward slicing to find all the related statements. And these related statements are defined as the vulnerability-related statements. And through the slicing algorithm, we can obtain a list of vulnerability-related statements, and then we define 5 types of mutation operators to augment the data based on the vulnerability-related statement and the vulnerability-unrelated statement. And the add mutation aims to rename the identifier in an assignment statement and add them back to the function. And the AI mutation aims to add an if condition, which is logically true, always logically true before the assignment statement, where this assignment is vulnerability unrelated. And the OO aims to reorder the assignment statement. And for the delete mutation, it aims to delete the statements that are not related to vulnerability. And for the RN mutation, it aims to rename the identifiers. And based on the mutation, we further proposed an edge-aware GGN for training the model. And this method incorporates the edge type information for GNN, which could further enrich the capability of the detector. And we use the edge type to encode the edge information and then combine both the node embedding and the edge type embedding for the message passing during the learning phase. And finally, a classification layer is used to make the final prediction. And during the training stage, we train a binary classifier to detect each type of vulnerabilities. And at the test time, we used each classifier to make a subsequent prediction. And the final prediction is then determined by a majority voting. The data set is shown in the table on the right upper corner. And we compare our approach with 7 baselines, including the static analysis to Valdi MVP and the deep learning-based approaches like multi-head attention, Divine, and Colbert. And firstly, we compare our approach with the baseline method. We can find the Valdi has less false positive samples, and it is quite reasonable because Valdi relies on the expert crafted features, and the recall value is lower than our approach. And this indicates the Valdi has more false negative samples, as these handcrafted features can only cover a very limited number of vulnerabilities. And the MVP have better performance than Valdi, but also lower than ours. And while comparing with the deep learning-based approaches, we find the Colbert usually has a better performance than other baselines, and it is because it is a pre-trained model utilizing a huge and massive amount of data for in the pre-training phase. However, the performance of Colbert is still lower than ours. And we further conduct an ablation study to evaluate the effectiveness of the proposed mutation operators. We can find, in general, incorporating these 5 types of mutation operators can significantly improve the recall and F1 scores. And those different types of mutations exhibit inconsistent performance compared to the original model. And lastly, we conduct the experiment to compare our Agile-aware GGN with some traditional GN, such as the GGN and GCN. To make a fair comparison, we only compare the result of different GN variants with the FG wild data now. And we can find the Agile-aware GGN, which encoded the edge type information, reduced the difficulty for the model to detect the vulnerabilities. And in conclusion, we introduced a fine-grained vulnerability detection, namely FG Wilddet, and proposed a novel vulnerability preserving data augmentation technology. And furthermore, we extend the GGN to an edge-aware variant to capture the edge information for the GGN learning phase in the task of vulnerability detection. So, any questions?
Questions?
You mean program analysis based?
Yeah, exactly.
Not yet. Not.
See the tables, the recall might be high, but the precision is not very precise. So have you considered to maybe combine or just compare with it?
We didn't done it yet because the motivation of this work is try to figure out how whether we can use a more specific vulnerability type as the detection, the target of detection, and then using a voting mechanism to reach a better performance. So basically, the methodology of the program analysis-based vulnerability detection is totally different from the learning-based approaches. So we didn't include that type of approach as our baselines.
Okay, any other?
That is a good question. Actually, if you check out the defined mutators, the mutation operators, you can find the semantics of these partial code remains unchanged. So that is a remaining the semantics unchanged, preserve the semantics unchanged is the basic tree. The basic tree. So, which means we won't propose do any mutation that could change the mutation. Change the semantics. Thank you.
Okay, so let's thank the speaker again. Okay, our last talk in this session will be presented by Diego Santos. He's currently a second-year PhD student at the University of Porto. He's currently working on holistic hardware-software partitioning for CPU, GPU, for CPU FPGA systems. Let's welcome.
So is this on the microphone? Yeah. So. Okay. 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 So today I'm going to present you my paper on flexible task graph representation and its generation from C applications. Open parentheses, work in progress. So I think we are all more or less familiarized with the concept of taking an hardware accelerator in order to improve the performance of a generic application. So I have an application that is running on a CPU, and I will try to find performance critical sections or regions in that application and offload them onto an accelerator to improve its execution time, energy consumption, and so on. And of particular interest to us are FPGAs, because they are very adaptable and can pretty much try to extract as much performance from almost any arbitrary piece of C code that you can think of. But the problem is that this mapping and trying to find these regions is yet a fairly unsolved problem. And typically, in order for us to find these regions, we need to model the application as a task graph. So what is a task graph? There are many definitions, but in essence, it is a set of tasks, so units of computation, and their relationship, which is usually in terms of data communication and data dependencies. And task graphs are usually built after a type of application. So for instance, if I have, say, something like a neural network, where I have function calls that implement each layer, then my task graph is probably going to represent the layers of the neural network. The problem kind of starts to arise once you want to generate task graphs from generic applications. You can't make any assumption about the organization of the application, its architecture, or anything like that. And so having a task graph where each task maps very cleanly into one syntactic feature, like a function, a statement, a loop, is very, very hard. And the other issue as well is that the problem of trying to decide whether a task stays in the CPU or is offloaded is also NP complete, because the more tasks you have starts growing quite exponentially. This problem is further worsened once you start to consider regions that go beyond these typical syntactical features. So for instance, imagine that I know a priori that the best region for offloading is a region that shares data with that variable called filter, which is a buffer. So I have a function, then I have a couple of statements, and then I have another function. How do I generate a task graph that can capture all of these different structures and actually tell me that these are the tasks that are of interest to us and nothing else? And furthermore, how can I do this while preserving the original source code? So this would be very easy if I lower this down to, say, LLVM or some other intermediate representation, but I want to keep the original source code because I want to generate HDL from it or target a GPU or something like that. And for this purpose, we propose what we call the extended task graph. So the extended task graph is an AST-based representation. So it uses the AST representation of the source code and doesn't break up that source code. It preserves its readability, its retargetability. So everything you do on the task graph is almost innocuous because whatever you do after is perfectly possible. And we want also to enable flexible task granularity. So our tasks no longer map to one specific syntactic features. We can actually take a task, divide it into smaller tasks, increasing their granularity, or join two or more tasks together into a larger task. And of course, we also want to make data communication between tasks very, very clear so that we know what the lifetime of the data that is shared between tasks is clear for us, because we may be very interested in selecting groups of tasks or clusters that share the same data, which is very important when you want to create efficient FPGA accelerators. And so in order for this task graph representation to be possible, we first need to convert our source code into what we call a normalized C code representation. So we take input C code, which can be written in any style with many different kinds of syntactic features, and we will, through source-to-source code transformations, reduce it down into this format. So our code only has functions, and every function is one of two types. So the first type are functions that only have pure computations. No side effects, no calls to other functions, no funny business with global variables, or anything like that. And the other type are functions that only call other functions. We allow some very basic control, so like if statements and for loops with a single level, so no nesting. But through extensive code restructuring, we can get an easy application within reason to map into these two types of functions. And so now that we have settled on a standardized representation of C code that we can work with, we can actually start to define the extended task graph. So in essence, our extended task graph is a directed acyclical multigraph, where each node can either be a task by itself, or it can be a cluster of tasks. So basically, we have graphs inside graphs inside graphs. And the edges represent the communication of data from one task onto the other. And as I said before, the extended task graph is an overlay of the program's AST. So everything we perform on the task graph is reflected on the AST and is always kept correct. So whatever we do on the graph will be reflected on the AST, and we can then generate code according to that. So if I have a function called f1, that will be my starting task, let's call it that. And then I have a call to f2, which is going to be mapped into its own task, f2. Then I have a loop with f3 and f4, and since f3 and f4 don't share data, don't have data dependencies, they can be each offloaded onto their own separate tasks, each with the 100 iterations each. The same cannot be said for this one, because F5 and F6 have data dependencies, so we will create a task for the loop in general with those 500 iterations, and then inside the loop, on a lower level of granularity, we will create the tasks. And then just another one for good measure. So in essence, all the transformations that we do on the graph will be reflected on the ST. So merging tasks is function inlining, and splitting tasks is function outlining. Furthermore, about data communication. Data communication is always done on the data item level. So a data item is basically a discrete piece of data with one or more names. So that one over there, filter, will always have a single path, which is called the read-write data path, which is a path that shows me where the data is modified, and it is always linear. But it can have a few spurs that represent tasks that only read that data and don't modify it. Yet again, about the changes in granularity. So imagine, for instance, that I have that very sequential, very small task graph, and I want to extract some parallelism. So I can take task T2 and split it into 3 separate tasks, T2A, T2B, and T2C. And what that is, which more to more task level parallelism, because I now have 3 tasks that can execute in parallel. And the matching operation in the AST will be that I will take those 3 statements and basically outline them into their own functions. This is a very basic example, just one statement. Of course, in a real scenario, this can be arbitrarily complex. Multiple loops, multiple functions, whatever you want. So, in order to kind of see how this task graph behaves using real-world data, we used some benchmarks from the Rosetta and the MaxWidth benchmark suites, and we generated the task graphs. And we see that around, we never have more than 20-something tasks per graph, which is an interesting number because it allows us to both increase the granularity of a task graph, increase the number of tasks a little bit more, because that problem with the exponentiality is still quite manageable at this point, or also to decrease the granularity and create smaller graphs. Then, about those read-write paths and read-only paths that I mentioned, we also took for each data item an average of their typical length, and we see that most data items only survive for about 2 tasks. So the lifetime of our data items in these benchmarks tends to be very small, which can then also further inform us about the kind of clusters that we can create around tasks that use the same data. Then, about the level of parallelism, so we gathered every subgraph in the task graphs and we calculated a measure of parallelism. So basically, the critical path divided by the total number of tasks in that task graph. And you see that for the most part, we have always a round of 2, which means that about half of the tasks can be parallelized out of the box. But there are still a few examples like that one with 1 that could maybe be a very interesting case where we could pick it and try to split the tasks, increase the granularity in order to extract more parallelism, because as it stands, it has none. And finally, also very important in the context of FPGAs is the percentage of total communication that is done through a producer-consumer relationship. So one task produces the data, the other one consumes it, and this is done linearly, which can lead to the creation of a data flow region, which can be very easily exploited by an FPGA. So finally, almost to conclude, let's talk about a little bit about the tool flow. This is implemented with Java, a source-to-source compiler, C++ and C++. It's the same as the one used in the Rust borrow checker that you saw 2 presentations ago. And basically, all that I've mentioned here is completely automated. So we have our code transformations, our task graph generation, our metrics and properties extraction, and in the future, also an actual partitioning engine that will create these code regions and therefore them into the FPGA, and then, of course, output the host C code and the accelerator C code already separated and ready to go. And so just drop everything around. We talked about the problem of loading an arbitrary application into an FPGA. We talked a little bit about the C standard that we need to have in order for us to do this. We talked about our extended task graph representation and a few properties that we extracted from it that will inform our future research. And that future research is exactly to perform a method that partitions and optimizes the code by doing a single pass over the extended task graph. And that is all. Thank you for listening. Okay, so in essence, that's still our current work. That's where we want to get to. This is just the representation that will allow us to actually export that. But ideally, we want to come up with an heuristic method that tries to balance in one way tasks that share the same data, the physical constraints of the FPGA, like the number of resources, and also the parallelism that is inherent within a cluster of tasks, which can or not be exported by the FPGA. So trying to come up with this, let's call it this magical formula, is basically the whole point of my PhD, which is still very much early days in regards to that. But this representation is already built with all of the information that we need in order for us to be able to reach that point someday.
Any other questions? Just in case.
Yep.
Why are we targeting FPGA? Because it's very slow.
Yeah, so we made some experiments with this, with actually some motivating examples where I did this by hand. And in fact, we did find that FPGAs, in the data center type, like when you have one of those PCIe accelerators running on data center, in fact, there is nothing much to gain when compared to the CPU of those machines. But once you get down to the embedded, where you have like a small, low-powered ARM CPU and a modest FPGA, things are much more balanced, and there is much more we can actually gain by doing this right. So a naive approach that would just select the kernel and let it run would still probably not be good enough, but by selecting regions that are a little bit more interesting, we can actually extract more than just running it on the CPU.
Okay, so this will conclude our session. Thank all the speakers.
So next, we're going to be the heart-pounding moment, the exciting moment. So we're going to announce the best paper award. Thanks for staying so long. This is thank you all. And actually, best paper award is just introduced this year. So previous years, we don't have best paper award. This is new for the 25th anniversary of LCTES. So we hope that this basically rewarding best paper authors as not only like recognition, as a recognition of their hard work, but also we hope we're going to inspire and motivate future submissions, especially high quality submissions, to make the drive LCTES to the next level. So we have a number of very high quality submissions. We wish we could give award to each paper, and unfortunately not. So this year, the paper, the selection of best paper is based on the reviewing scores, reviewers' expertise, and also online discussions, and also the organization committee check the paper's quality based on their significance, soundness, novelty. All this has been have been factored in. So without further ado, so I'm thrilled to announce the best paper award goes to Tenisec. Join me to congratulate the authors. I think Sony is the only author came today. So congratulations, well done. Would you like to come this way? And a few sentences about contribution about this paper from Will.
Yeah, so this paper presented two very good optimizations to accelerate machine learning models. One was spilling long lifetime sensors, like long defined to use or used to use time tensors, and so spill it in the outside memory and then load it back when it is needed. And the second was to, instead of merging tensors, you update them in place. So the reviewers particularly liked the first idea a lot, and they also appreciated the second idea and the experimental results. So congratulations.
Anyone would like to help her to take a photo?
We already stand up for that. Thank you, JJ.
Thank you. Thank you.
Congratulations.
Congratulations.
Thank you all. Hopefully, we're going to see you next year.